Hello? Sir, you are not audible.
Yeah, we are going to start now. Hello.
Hello?
Hello.
So sir, good morning, sir.
Good morning.
How are you, sir? Hello.
Hello. Good morning. Hello.
Sir, am I audible? Sir, am I audible to you, sir?
Yeah, you are audible. You are audible.
Okay, sir. Okay, sir. Thank you. Thank you. Okay, so sir, shall we start? Hello.
Yeah.
Okay. Okay. So good morning, all the participants. Today I, Dr. Narendra Kumar, welcome you all on the second day of STC, that is on Industry 4.0 and Smart Manufacturing, Opportunity and Challenges. So in today first talk, Professor Pulakmon Pandey sir from IIT Delhi will deliver the talk on the role of additive manufacturing in Industry 4.0. So before we start the talk of sir, so let me share some brief about the Professor Pandey. So Professor Pandey completed his BTech degree from HBTI Kanpur in 1993, securing first position, and got master's degree from IIT Kanpur in 1995 in manufacturing science specialization. He served HBTI Kanpur as faculty member for approximately 8 years and also completed his PhD in the area of additive manufacturing from IIT Kanpur in 2003. Then he joined IIT Delhi as a faculty member in 2004 and is presently serving as a professor in IIT Delhi. So in IIT Delhi, Dr. Pandey diversified his research area in the field of micro and nano finishing, micro deposition, and also continued working in the area of 3D printing. Till now, he supervised 30 PhD and more than 34 MTech theses in last 10 years. And also he has filed 17 Indian patents. He has approximately 154 international journal papers and 45 international national referred conference paper to his credit. These papers have been cited for more than 5,000 times with H index of 35. He received highly commended paper reviewed by Rapid Prototyping Journal for the paper fabrication of three-dimensional open porous regular structure of PA 2200 for enhanced strength of scaffold using selective layer sintering. So this paper was published in 2017. So many of his BTech and MTech supervised projects have been awarded by IIT Delhi, and also he is also a recipient of Outstanding Young Faculty Fellowship, IIT Delhi, sponsored by Kusuma Trust and J.M. Mahajan Outstanding Teacher Award of IIT Delhi. His students have won the Gandhian Young Technological Innovation Award in 2013, 2015, 17, and 18. So it's a great privilege, pleasure for all of us to have Professor Pandey. So now I invite sir to start his talk. Sir, please.
Okay, so thank you very much, Professor. Before starting, I would like to thank, the administration of NIT Jalandhar, the organizers, Professor Aviral Mishra. I think he is one of the coordinators, correct?
Yes, sir. Yes.
Yeah. So my talk is, my main research area is 3D printing, that you also know nowadays additive manufacturing. And additive manufacturing is something which is a key technology which has been projected in case of Industry 4.0, or which is also known as smart manufacturing. So I'll start my lecture with an introduction to this additive manufacturing, and then I'll take you along the why really the 3D printing or rapid prototyping, or what you call as additive manufacturing, is important tool which is to be used in smart manufacturing. And then also I'll tell you about that how in the environment of additive Industry 4.0 smart manufacturing, how this additive manufacturing can be used for managing the maintenance activities, and how it is helpful in supply chain for the various automotive maintenance and the supply chain of the spares basically. So let me share my screen, and I can see that there are so many people, so many participants in this meeting. There are around 196 I can see, and
sir, we have 1400 registrations. Sir, we have 1400 registrations. Sir, we total 1400 participants have registered themselves to attend this
how many?
course.
1400.
Yes, sir. Yes, sir. Yes, sir.
That is too big, huh?
Yes, sir. Yes, sir.
Okay, so my screen will be coming, I think, now.
Let me check. Yes, sir. ATC. Okay. Fine.
Is it visible?
Yes, sir. Industry 4.0, the fourth industry revolution. Yeah.
Yeah, so I'll first try to explain that what is really the smart manufacturing or Industry 4.0 is, and then I'll talk about why additive manufacturing is important here and what is exactly additive manufacturing is. So let's try to understand this revolution, the industrial revolution, correct? So we all know, everybody I think present in the meeting might have heard about invention of steam engine, James Watt steam engine, correct? Everybody knows about it. So if you see on number one point. This number one point, if you see, this is the engine which has been shown here. It is the James Watt steam engine. Now, actually, this James Watt steam engine, when it was designed and finally fabricated and brought to the action, that brought the first industrial revolution in the history of industrialization. Correct. Now, why it brought the first industrial revolution? Because before really this was developed and brought into the action, the people used to use either the muscular power of humans or cattle to drive the various systems, those primitive systems or machines which might be there at that time. So people used to drive those systems or machines using muscular power or power of cattle. You might have already seen that there's something called rahat. What is that rahat? Rahat is a machine, or you can say system, which is used to take the water out from a bore well or from a pond. It's a rotating wheel which has number of buckets, and that rahat is being operated by the bulls. And then when that rahat moves, circulates, the buckets, the water is taken from the bucket and it is being poured in a outside on a little higher altitude, and it is used for the something called irrigation purpose. So that even I have seen in my childhood in my village that people were using that kind of thing for irrigation. So that was a cattle power which was utilized. You might have already seen that bulls are used to plow the fields, correct? So there are a number of such examples which can be given where cattle power people used to use, correct? So this introduction of steam engine into the industry, that was the time and is known as mechanization, because the muscular power was replaced by the steam engine, and or maybe sometimes water power, that was a sometimes steam, that was a turbine kind of thing. So it introduced a new manufacturing kind of thing. Of course, the iron production was also one of the key element which happened simultaneously. There was a little growth of textile industry, mining and metallurgy, and the machine tools were driven by the steam engines or sometimes by the water turbines kind of thing, and the steam factories were developed. So all these things together brought actually the first industrial revolution in the society. So in first industrial revolution, basically the muscular power was replaced by the steam power. Now the second industrial revolution took place when people tried to do basically the mass production or the continuous line production, correct? So you might have visited some industries like maybe Maruti or Honda. You might have seen the assembly line. There's a continuous assembly line that is a backbone of actually mass production, correct? Because if you have to produce 1,000 or 1,200 bikes every day, then it is only the way that helps you. So technological electrification, production line, mass production, globalization, engine turbines, and broad adaptation of telegraph, gas and water supply. This has actually brought the second, this is said to be the second industrial revolution, where people started multiplying, rather doing the mass production using the various means as listed under point 2. Now the third industrial revolution took place around 1970, we can say, when there was a development of microprocessor, correct? Means or you can say, if I want to be little vague, I can say when the electronics came into the picture, correct? So when there was a development of microprocessor, people have started using microprocessor for automating, correct? So for automation, and that has actually led to the substitution or reduction or elimination of the human mental effort. So in industrial revolution one, people have in society the muscular energy or power was replaced by the steam energy or power. But in third industrial revolution, it mental energy, or you can say the mental efforts by the human beings, that was replaced by the microprocessors. So that has actually became possible because of the development of computers. Lately, we can say internet, which is something which has come around, I think around 1995 or so. Digital manufacturing, that is NCCNC, PLCs, robotics, information technology, OT, digitization, automation, digital network, digital machines. So basically, this if you see the things which are written below point 3 is nothing but they have replaced the human mental effort. So that was the industrial revolution 3. Now today if we see the ages of IT, there's a lot of digital information available and there's a lot of communication technologies which have emerged out. So this Internet of Things, then convergence of IT and OT and autonomous machines, advanced robotics, big data analytics, optimization, artificial intelligence, augmented reality, all the concept of cloud and cloud computing, cloud smart factory, machine learning, AI, the cyber physical, all these things, if it means if the machines, the digital machines which were described under point 3, that are under third industrial revolution, if they are communicated, if they are integrated and they can communicate with the aid of information technology driven through artificial intelligence, machine learning algorithms, and use so many other advanced concepts which are related to internet or information technology, then that kind of manufacturing scenario is said to be smart manufacturing or industry 4.0. So I'll explain the things a little more. So from this slide, once again I want to give you the picture that this industrial revolution 1, that was first industrial revolution, that was introduction of mechanical production machines powered by water and steam. That happened at the end of 18th century or beginning of the 19th century, correct? Then you can see that this thing has taken around 100 years, correct, to come to the concept of mass production. That was the beginning of 20th century. And then beginning of 1970, that was early 21st century, we can say, the industrial revolution took place, which was through the use of electronics and IT further progression in autonomous production. And the industry 4.0, which is the most modern concept today, is based on the cyber physical systems and cyber physical system, machine learning, artificial intelligence, big data, and so on and so forth. So I'll tell you the things in my forthcoming slides. So you can see here, it is the level of complexity which has been shown, and the things have been described through various pictures, correct? So in the very first one, you can see that there are certain machines which are very simple machines which were driven through water power or steam power. Then there is a concept of continuous production. Then a robot has been shown which is doing welding. So that is the use of digital manufacturing. And when this digital manufacturing is integrated with IT and cloud-based controls and computations, then it becomes a cyber physical system. So like here, what has been shown, that somebody is trying to control the machine using using an app which is developed in a which is actually in a mobile, correct? So the various machines are being controlled with remotely. That kind of thing is there. So actually, it is a big umbrella. So many things are there. So I try to cover the things. Okay, so what? So the backbone of Industry 4.0 or smart manufacturing is cyber physical system (CPS). Correct. So what is cyber physical system? From this figure which has been shown in this slide, you can have a look that it is actually in the core there is information. This is the digital information which is in the core. Now, if you see, go back to the third industrial revolution, here, the concept of information technology was not, much, or it was not there. Like there was no information technology that was there in the 70s, or till I will say even the concept of information technology has been introduced around 2000 or even after that. So, in the core, there's information technology. You need to do the computation, lot of computation. There's a huge chunk of information, correct? This information is a digital information, and if you want to use that information, you have to dig out the relevant information. You have to find out the relevant information from the huge information, and then you have to also do certain computations, correct? This is a big data, and then there is the analytics. You have to take decisions basically, and for taking a decision you sometimes require, or like most of the times you may need because there are very many options available, so you are going to use one option which is optimum for you. So you are going to use some algorithm. That algorithm may involve sometimes optimization, or sometimes if the information is scattered and you are unable to do the optimization, you need to develop some model that may be based on machine learning or artificial intelligence, and then definitely you are going to perform the computation. So information is to be basically, if you want to use the information, how optimally you are going to dig out the information, how you want to process that information, how you want to arrive at a optimum information, that you will do in computation. And then there will be communication. Communication means this information has to communicate very efficiently without loss of data, with security, to a particular manufacturing system, correct? That this information will be used to will be communicated, and then the manufacturing facility or the manufacturing system that will be operated, and that's why you need to have a proper control on that, correct? So this whole thing together actually constitute cyber physical system, correct? So what is the cyber physical system? The cyber physical system is a system of collaborating computational elements and controlling physical entities, correct? So basically you are computing, you are communicating, and you are controlling the physical entities, which are basically machines, which are production machines in your case, and in case of smart manufacturing, this physical entity or the manufacturing machines are actually the additive manufacturing machines which have been recommended. So CPS are physical and engineered systems whose operations are monitored, coordinated, controlled, and integrated by a computing and communication core. They allow us to add capabilities to physical systems by merging computing and communication with physical processes. So this is the definition of cyber physical system, and this is through this figure you can have a feel of the system. Though I can tell you it is very difficult unless somebody jumps into the pond, or you can say jumps into the ocean of this philosophy, or you can say the technology and start swimming and trying to learn so many things every day, then only you will have a real feel of the thing. Okay, then let's try to see that what is today's factory. Like the today's factory is something which is based on the continuous production, a system, continuous assembly line kind of situation. So there are basically various workstations, correct? Like these various workstations may be manufacturing workstations, they may be assembly workstations. So they are rigidly sequenced car manufacture on a production line, which has been shown in particular slide. So there are workstation 1, the workstation 2, 3, 4, and there are so many workstations. So many workstations are there. They are either manufacturing or assembling, and basically you can see that they are rigidly sequenced. Correct. So finally, you are getting a automobile, assembled automobile, and this is what I believe that most of you, if you have visited any automobile company, maybe in outskirts of NCR, you might have got a chance to understand and actually see this today's factory. Correct. Okay. Now, what is the new concept? The new concept of smart manufacturing. That is the tomorrow's factory. So this tomorrow's factory is actually decoupled, fully flexible, and highly integrated manufacturing. Now you can see here that there's a no line kind of thing. Rather, you have different workstations which are decoupled, but they can communicate with each other, and they are flexible. Flexible in the sense that there will be a design flexibility, there will be a manufacturing flexibility, there will be a flexibility from changing from one kind of product to another kind of product, and but at the same time they are highly integrated. So integrated means they are they talk, they are able to talk with each other, they want to communicate with each other, and they want to assist each other, and that's why they are basically, though they are decoupled, their location may also be different, but they are highly integrated also in terms of data, in terms of information, in terms of communication, in terms of controls. So then you are actually doing the production, and you are getting the same thing as output. Is the concept of tomorrow's factory, which is known as smart manufacturing. So in smart manufacturing, there are 6 design principles. Correct. Now these design principles are interoperability. What does it mean? The ability of cyber physical system, that is workpiece carries, assembly stations and products, human and smart factories to connect and communicate with each other via the IoTs, Internet of Things and Internet of Services. So that is known as interoperability. Then virtualization, a virtual copy of the smart factory, which is created by linking sensor data from monitoring physical processes with virtual plant models and simulation models. Then decentralization, the ability of cyber physical system in the smart factories to make decisions on their own. Correct? That is the concept of decentralization. And then there's a real-time capability. The real-time capability is capability to collect and analyze the data, that is the information which is present, and provide the insights immediately. So if you want to definitely provide the insights immediately, if you want to reach at an optimum solution immediately, what you have to do is you have to probably use the various algorithms that is actually the computation, which may involve artificial intelligence, machine learning, and so many other things. I think that in this particular course, what I'm talking, like IoTs, Internet of Services, optimization, and maybe we can see that this machine learning, etc., you will have definitely some glimpses, maybe if not much, but definitely some of the speakers will be talking in deep about, a little deep about, because in such courses one cannot go in very depth. You need to do some workshop kind of thing on machine learning or AI, where you can really understand such things. So there's a real-time capability, the capability to collect and analyze data, and service orientation, offering of services via Internet of Services. So, like like suppose you want to produce, there's a need of a component, correct? I will explain this thing when I will talk about the maintainability aspect using additive manufacturing for Industry 4.0. This thing will become more clear. That is the service orientation. And then modularity. Modularity means flexible adaptation of small factories for changing requirements of individual modules, correct? So there's a modular designs. So basically, if there are modular designs for a particular set of customized product, I will say, then these manufacturing systems will be able to take appropriate decision accordingly, and there will be a flexibility in the manufacturing system which can adapt to the various modules for a particular class of product for manufacturing. Okay, so what are the building blocks of Industry 4.0? So like there are various, like here I have shown 3, 6 and 8 various technologies, correct, which together forms the backbone of Industry 4.0. Obviously, on the center, or you can say, we have to see from here Internet of Things, Internet of Services, correct, and then we have basically cyber security, because we can see that horizontal and vertical system integration, that is the decentralization. Then once you are doing everything, designing and manufacturing, that is in digital mode, there will be a simulation that is needed. There will be robots. There will be big data, I have already explained. There will be augmented reality. What is augmented reality? Augmented reality is like, I'll give a very good example. Virtual reality is something like you play games nowadays. You are playing like PUBG kind of games, correct? So there's a virtual reality. But suppose you have been given a system to wear, correct? You have been given a system to wear, and once you wear that system, you see that there's a big green ground field in front of you, maybe 100 square meters field is there, and there are many deers which are running around. And then you have a gun in your hand and you're trying to shoot that deers. So actually the gun is original. The gun may be original sometimes, and you are actually shooting, but there's no deer actually. It is just a virtual deer. So there's a partially it is actual, partially it is virtual. So that kind of system we can think of as an augmented reality. One example in manufacturing I would like to give, that suppose you wear that kind of system, and everybody, I think in this meeting, you might have tried to do this virtual simulation of CNC machining, correct? There are softwares like Power Mill, or there are some other softwares where we try to develop a software, CNC machine software, and on computer screen we can simulate that how really the machining is taking place, and we are able to perform the things. Now suppose we are given some device to wear, and we are actually standing in front of a machine, and I can see a workpiece being set up on the work table. The CNC machine is actual, but the work piece is actually virtual, and we are actually doing the programming on the console of actual CNC machine. The tool is actually moving, and you are observing that work is being cut, but there's nothing in actually there's nothing which is being cut. So such kind of system, if you develop, that is known as augmented reality. Now you can see here that additive manufacturing, which is also known as 3D printing, is something which is suggested to be a building block of Industry 4.0. So here I am going to emphasize now another maybe 1 hour of lecture which I have. I'll talk mainly on additive manufacturing, because additive manufacturing is, I'll say, a manufacturing process which is not 100%, but it is quite automated, correct? So there's a skilled operator or maybe engineer is needed to drive these manufacturing systems, but they are quite automated and they are driven by digital data. So that may be the reason why this additive manufacturing has been suggested to be an important tool or a building block for an Industry 4.0 or smart manufacturing. So like the concept of Industry 4.0 smart manufacturing is a digital enterprise. It's complete digital enterprise. That entire value chain is digitized and integrated. Like you can see that there's a transition from digital world, which is a virtual world, to the real world, correct? And this transition we are achieving through product design, production planning, production engineering, actual production, services, correct? And you can see here that if you need to do simulation, you have to do product life cycle management, you have to execute the manufacturing systems, you have to integrate all the systems together, and then there will be a life cycle data driven services for maintaining your products. So that's how you are actually approaching from digital world to the real world, and that's the kind of concept which is there in smart manufacturing. So today we are talking about top 10 skills to be relevant in Industry 4.0, correct? Like you can see today we are in 2020, correct? But this is a little old slide which I have picked it up from some source. The source has been given below. So I always acknowledge the source, because most of these slides which I have shown you today, they have been picked up from some sources, and every slide has been acknowledged, has acknowledged the source from where it has been picked up, and this entire story which I have developed around these slides may give you a good picture of what smart manufacturing is, but I can tell you it's not that simple. Obviously, it's a big ocean, and it's an integration of from very scratch, very fundamental technologies to very high-end technologies like Internet of Things, communication, and maybe the machine learning kind of things. So the manufacturing of today, that's we can say the continuous manufacturing, it requires these kinds of skill sets. What are these skill sets are? These are complex problem solving ability, correct? What is complex problem solving ability? You all know that. There's a lot of we all know about the JEE examinations, correct? The purpose of JEE examinations, JEE advanced examination, is to verify or to establish that the student who's coming to some premier institutions like NITs or IITs, they have an ability that they can solve a complex problem. Their mind is application oriented. They can actually apply what they learn to a real world problem. That is what is complex problem solving. Coordinating with others. So this is related to teamwork. You cannot run any organization like NIT, IIT, or maybe any industry without coordination, correct? So coordinating with others is very important. Management of people, you all know that. I believe those who are working in any institution or industry, they understand how complex with the people. I believe this is the most complex thing. Critical thinking, negotiation, you have to always negotiate, correct? Maybe that you can also call as trade-off. So you have to take decisions based on trading off. Quality control has to be there. Service orientation has to be there. Judgment and decision making powers have to be there. Active listening. You should be able to listen others and learn from that. And then definitely there has to be creativity. So these these are the 10 skill sets which are I believe covering the various things which are either taught to us or they are being inculcated on us based on the education which is being imparted to us from our childhood till maybe the engineering or graduation. And then, but what is actually needed? There are few points which you will find that they are little different in terms of skill sets which is needed in the smart manufacturing scenario, because in smart manufacturing scenario the involvement of humans is minimum. That's the whole problem. And then the controls are through virtual means, correct? So algorithms. So again, obviously the complex problem solving ability that has to be there. You cannot. So it is there. Critical thinking has to be there. Creativity has to be there. Correct. Then people management will become more critical because there are very less people and they are highly knowledgeable people having a lot of knowledge of advanced technologies. Coordinating with others, these things you cannot eliminate. Emotional intelligence. Now this is a new point. Why? Because you can see today's problem. You can have a feel. Today everybody is isolated, correct? Because of this corona. And once you are isolated, you are sitting in your home. Earlier, if I would have been addressing your this meeting, I would have traveled from Delhi to Jalandhar, correct? I would have met many people. I have seen many shops. I might have stopped at food courts in between 2-3 places because I have to travel around 600 to 700 kilometers on a taxi, correct? So that's what our behavior is. Now today we are in the COVID situation. We are sitting in one room. We are isolated. We are not going anywhere. We are meeting very limited number of people or sometimes nobody. So there are problems, correct? So that is emotional intelligence is needed because the number of people whom we are going to actually interact will be minimal. Judgment and decision making power has to be there. Service orientation has to be there. Negotiation you cannot eliminate, and there has to be a lot of cognitive flexibility. This picture, if you see in the bottom, it talks about the cognitive flexibility. Now what it shows a brain actually, correct? And the neurons has been shown, and these. I believe what is cognitive. I am trying to explain the way I am understanding it. This particular concept. Actually, like if you see today, what happens is that even when I'm sitting in my home quietly, and I'm guiding maybe 15-20 students at a time, PhD. So all those 20 problems keep on going in my mind, and sometimes some thought comes, sometimes some other thought come, and I have to think on number of problems together, correct? So how to switch over from one kind of problem which may be in unconventional machining, other problem may be in 3D printing, third problem may be of machine learning, fourth problem may be of computer aided design, fifth problem may be of machine tool design, sixth problem may be of stress and strain constitutive relationship, and seventh problem may be of solving of Navier-Stokes problem, CFD problem. So many problems together, correct? Because you are actually dealing with lot of digital information, lot of big data, lot of algorithms, different kinds of problems. So emotional intelligence and the cognitive flexibility, they are the very important aspects and the skills which person has to have. Otherwise, there will be a situation which may not be very promising and pleasant. So this is a lot of things which actually industry 4.0 is something which is bringing in your way. Now, once you are taking this industry 4.0, you are applying to your industry, how really it is going to impact, correct? What do you think? It will impact individual? It is definitely, correct? Everybody will be affected in a positive manner also, in negative manner also. Then society, because individuals make the society will be affected. Then your nation and the globe, in everything, that will be affected. Your business will be affected, and that's why your economy, the world's economy, will be affected. That's how this you all know that manufacturing is something. If we go to the very basic definition of manufacturing is something which governs or which influences the GNP, that is the gross national product of the nation of any country, and it governs the economy of any country. So that's why the global economy or economy of various nations will be actually affected if you try to adapt and bring this smart manufacturing in your organization. So this is first part of my lecture. I will take a break of 5 to 10 minutes, and then I will come back and I'll start that how really additive manufacturing and why additive manufacturing is important, and why it is what are the features of additive manufacturing which makes it very potential, very novel to be used as a tool in smart manufacturing. So if there are some questions I can take in this part of my lecture, and then there will be then I'll switch over to another presentation on additive manufacturing and how it is definitely useful in industry 4.0. Correct? So if organizer who's there, who's coordinating?
Yes, sir.
So please, if there are some questions in this part of my lecture, you may ask the users, candidates to ask.
Okay. Now let me check the chat box if any question is there.
So Aviral is there in this meeting?
Yes, sir.
Yes, sir. He is here.
I am present, sir.
Maybe both are here. I think till now, sir, there is no question.
Okay, so you could understand everything, eh? People have understood everything?
I hope so, sir. Hope so.
Participant, if you have any question regarding the last that section, then you can post your question on the comment box. So one question is there from Somesh Singh.
Yeah.
Sir, what will be the effect on the job due to IoT?
Internet of Things.
Yes, sir.
No, Internet of Things has actually, what is Internet of Things, correct? So Internet of Services, Internet of Things together, like if you see this e-marketing which you are seeing, correct?
Yes.
This e-commerce which you're seeing, that is a combination of IoT and iOS. Is it fine? So you yourself can understand that they are creating some jobs, they are also taking away some jobs. Is it okay? So some new kind of jobs are being created and traditional kind of jobs are being taken away. So there are that kind of scenarios there. So one cannot say that it will take away the jobs or it will create so many of jobs. Rather, the nature of job has changed. This is what I feel.
Yes, sir. I think the skill set required for a particular job may change,
Yeah.
but I think job may not go
Yeah.
accordingly. So one question is that why our industry not fully use Industry 4.0?
Yeah, this I think I'll answer a little later. Actually the reason is we are actually this why Industry 4.0 is a very modern concept. Correct? Like only few 1-2 industries in actually in US and US in they called it as smart manufacturing. Germany, in Europe, they have called it Industry 4.0. So Industry 4.0 is something called a clean, extremely clean environment. Like like if you see an industry which is as clean as a Max hospital, is it okay? And everything is digitally operated, then it is a Industry 4.0. Now the answer you yourself can understand that what kind of situation is there in various countries, in our country and in other countries, which are either developing nations or they are not even that developed that we are. So even there are many small scale industries or even the modern industries in our country. Those they are not having, they could not use this concept because there's a no backbone. Lot of investment is needed, lot of planning is needed, lot of infrastructure is needed. Correct? Capital investment, infrastructure, and then there has to be a people. There has to be skilled people who can do it. And it is not Industry 4.0 is not a machine that you can purchase from Germany and you can keep in your plant and it becomes Industry 4.0. No, it is a philosophy actually. So it is you can say it's a technology also, but the technology is highly integrated with various technologies. So for your particular industry, you have to develop it. There has to be engineers who are very much motivated and innovative and have spirit to do it. And then there has to be a lot of funding. There has to be a lot of time. So that's how you can do it. So it's not as easy that you bring a CNC machine from some country, Poland or maybe some Germany, and start in your keep it in a room and start making the thing and say it is Industry 4.0. That is not the case. I think I have answered.
Yes, sir. Yes, sir. So one question is that what else skill sets are being required for today's generation to come up with present Industry 4.0? I think we are talking about this only in the lecture.
I have given that slide. So in slide, the 10 skill sets have been written, correct? So obviously those skill sets are needed. Do you think that like anything else is also required? So what is the question that what like somebody can think and tell some word? I can give some answer, but that is not that is not actually required. So the 10 skill sets which are well thought of for Industry 4.0 that I have already told. So what is the doubt? I am not able to understand. If there is any doubt in those sets, then he can tell. Or if he has any other skill set in his mind, he can tell. Then I can explain to him. Like, yeah, this I can see the question of Sampath Patel M. What else skill sets are being required for today's generation?
generation to up.
Now I'll tell you. Actually, you should know good mathematics, critical mathematics, physics. You should know. Science background should be good. You should know a lot of programming. Correct. You should then learn the softwares, then you should know how to develop algorithms, correct? And then you should be able to integrate these things with various mechanical and electronics elements. So if this kind of data set you develop, you will have one step moved towards industry 4.0, correct?
Yes,
But
yes,
nowadays, what we see, student just want to learn, they mug up the things, and they take a small desi book, and they read it, mug up it up, and write the exam and get some marks, and they feel that they have achieved everything. That is not the case.
yes,
Just passing the examination. Suppose you are learning a course on computational method, correct? And you are solving the problems by hand, Newton-Raphson method, or maybe an optimization algorithm. You are doing 4 steps, not making any program, and you are not doing any real life problem. You are not solving. You are not automating the process. Then you are not moving towards learning this industry 4.0. Correct. So there are so many things. You have to be quite good in terms of programming and critical complex solving ability. So that's how you have to make. So, Mr. Sampath, what is your qualification?
uh, Mr. Sampath Patel M.
You are a faculty. Is a faculty somewhere?
I don't know actually at this moment. I can't tell actually.
Yeah. So he can interact with me if he want a very specific answer for his own uh, perspective. Then I can answer him separately. Also. There's no
So I think you have answered because there is a huge combination of technology, IT, electronics, mechanical, and when we combine all these three into being, then we can move forward
then
to the industry
yeah,
4.0.
then there should be skill of taking people along and doing the coordinating with them, and also uh, able to have a collision and come up with a proper solution for any problem that may involve multidisciplinary things, maybe computer science, artificial intelligence, electronics, mechanical engineering, maybe some other social and different kinds of aspects. So I think let me take a break. This is already 10:57. Then
Yes,
I will have 30 minutes time to explain additive manufacturing and its aspects. Is it
yes, sir.
okay?
Yes, sir. Yes, sir. Fine,
Okay,
sir.
so 11:05. Let us meet at 11:05.
Okay, sir. Dear participants, we are taking 5 minutes break, and we will come back at 11:05. Kindly be with us.
next part of the lecture.
Yes, sir. So please, sir.
Yeah. Okay, so here basically I'll try to emphasize the what is 3D printing principle, what is additive manufacturing printing principle and its application, and then I'll try to in 10-15 minutes, and then I'll try to tell you that why really this is useful in industry 4.0. So the principle is very simple. Like let me try to explain you what is the 3D printing or additive manufacturing. Like suppose you want to produce a product like this. Is it all right? The product like this you can do by machining. You all know that you can remove the material layer by layer and you can make this component, or you can take two blocks. If it is a simple product like this, you can weld them, join them, and you can get the product. The third approach, maybe you take a bulk of material and forge or deform this material plastically in a die, and you will get basically the component. This is called forming process. But here this is the approach. The approach is a bottom-up approach. The bottom-up approach, you are actually depositing the layers from bottom to the top, layer by layer material deposition. This is known as 3D printing or additive manufacturing. Now in additive manufacturing, what do? We try to actually first we do the CAD modeling, correct? So this is the important point to be noted, because in industry 4.0 you are trying to find, you are actually doing everything digitally, correct? So once you are doing everything digitally, you are ultimately ending with a digital design. Now once you end with a digital design of a product and you are thinking that how to produce that product, what you will do is you actually have a digital design which is in the form of CAD model of the component, correct? So once you have like a CAD model of the component, you can tessellate it. Tessellate means forming the STL file. You will make the STL file of the component, and then you can slice that particular tessellated file. So slicing is nothing but intersection of horizontal planes with the STL file. So you basically get the sliced data, which we call as the layered model. It is a digital layered model, which is the sliced file. Now this digital information you can feed to any additive manufacturing system, which may be 3D printer, maybe some process, correct? So this 3D printer will actually calculate the various laser scanning paths or material deposition paths. So this calculation will be either done by the AM system software or by some freeware software which is available outside. So this step actually depends on the kind of additive manufacturing system you are going to use. So this digital information of slices will be again computed based on the kind of 3D printing technology you are using. So this will actually give you the physical model. So that this 3D printer gives you the physical model. Now this physical model you are going to post process, and then you are going to have the physical prototype with you that is either acceptable, or if it is not acceptable, you are going to do the little modifications in your design and redo the additive manufacturing. So that's what is the importance. Now here let me just demonstrate you that in additive manufacturing, suppose you have to produce a component like this, then this is called tessellation. This is tessellation. Tessellation means various surfaces which are present with this particular component, they will be approximated by small triangles, the way it has been shown in this particular diagram. So this size of the triangle becomes important. If you have very small size of the triangle, the number of triangles needed to approximate the surface will be very huge, and the time of computation will become very huge. But at the same time, if you are having if you are approximating with very large triangles, then it's not good, because you are going to lose the things, because the intent of the design will be lost, and you will be quite away from the actual design. So when you slice, actually it results into polygons. They are nested polygons from top to bottom. You try to slice the data. This is the actually graphics, but it is being written in the form of SLC format or CLI format. SLC is related to slice, and CLI is called common layer interface. So these are basically polygons which are written in certain format and which are acceptable by the 3D printers. Now generally we have three kinds of technology on which the 3D printer works. One is liquid-based technology. Stereolithography is one of the example for this. Powder-based technology is selective laser sintering or melting. Solid-based technology are like fused diffusion modeling. So what do we see? Then what is post-processing? So I'll tell you these processes in short. Now in post-processing, the most important one is post-curing, which is actually needed in case of stereolithography, because you are using photosensitive monomer to sinter, to polymerize by exposing it to the laser power. And then because it is a additive manufacturing, so if there's an overhanging feature, you have to deposit the support structure, and later on you are supposed to remove the support structure. And because there is stair-stepping effect in 3D printing components, so what is stair-stepping effect? I can show by this picture. So this is called stair-stepping effect, correct? Because you are depositing the layers in finite thicknesses. Instead of getting a surface like this, you will get a surface like this. This is called stair-stepping effect. So if the layer thickness is very fine, the stair-stepping effect is not dominant. However, if the layer thickness is little larger, you will see a dominant stair-stepping effect. So you can improve the surface quality by sanding or polishing or by painting. So we call it rapid prototyping. Earlier we used to call it, but what happens is that in a very short span of time, from a virtual model which is designed, you have a actual 3D printed, manufactured, fabricated, whatever you call, component physically available to you. That is the potential of these processes. So let me talk about now the processes, correct? So what is stereolithography? I will talk about, so this stereolithography is a process where we deposit the material. Here the starting material is a monomer. It is a photosensitive monomer. It is a liquid. It is a monomer liquid, and the property of this liquid is that if laser is also light. Laser is a light which can be focused at a very small area, but laser is actually a light. So if light above certain threshold frequency, E is equal to h nu. Nu is the energy of the HQ is the energy of the photon, and nu is the frequency. So h is Planck's constant. So the energy of a photon depends on the frequency nu. So if light above certain threshold frequency falls on this particular monomer, then wherever this light falls, below there you will find that there is a polymerization reaction that starts, and the material cures. It becomes from solid to liquid to solid. So what is being done in first, you pour here liquid equal to this layer, and the laser comes from the top. This mirror rotates, and wherever the laser spot goes, there you will find that this layer becomes hard. Then this platform moves down. Again, you will get the liquid inside equal to next layer, and again the laser will come from the top this all calculation has been done digitally, correct? They've already done this digital calculation. These mirrors moved by numerical control can deflect the point like this, and you are able to cure the material. So basically every layer you are depositing from bottom to the top, and if you have an overhanging feature like this, you are depositing a support structure. That is what is inherent characteristic of any 3D printing system. So stereolithography was the first additive manufacturing process which was patented in 1994, and it has advantages like its resolution is very good. Being liquid, you can deposit very thin layers. Its accuracy is quite good, and its surface quality is quite good. You can make transparent components. You can even make some colored components, but only the limitation here is that it needs secondary curing also, because it is a liquid, correct? You have to post process this component. You have to take from here and keep it in the oven for some time. That is the secondary thing you have to do. And second is you have to make a support structure. And third is the photosensitive monomers. They are very limited in numbers, so the choice of materials is very, very less. That are the limitations of this process. Now then we have another process which is called powder based process, selective laser sintering or melting. This is also known as powder bed process, correct? So here we coat the material, like again there's a platform, the platform can go down. So the powder is being coated like this. There's a powder spreading by recoater. Powder is spread around say 150 micron layer is spread. Then again the laser comes from the top. So the laser moves on this, and wherever the laser goes, this powder particles, they fuse together and they become solid, correct? So this brown portion which has been shown in these slides is actually the solid components. Then the platform moves down, and you again record the next layer, and again you perform the process. This is called selective laser sintering process. If we are using polymer material, polymer as a material, like polyester as a material, and if we use metal, if you are using polymer as a material, this environment is generally a nitrogen environment. But if you are using like steel powder, if you are using aluminium powder, aluminium alloy powder, if you are using say copper powder, if you are using some titanium medical grade alloy powder, then the gas which is used here is argon gas, because you need an inert gas, and the temperature ranges are quite high. Like in case of temperature, that you work around 300 maximum, but in case of metals you have to go sometimes 1200 to 1300 degrees Celsius if you're talking about sintering of titanium and so on. Then this is the printer which I think you might have seen. This is called fuse deposition modeling. Here we are actually using this wire, correct? This is a wire. This wire is being used, and this is ABS wire, thermoplastic wire. This is drawn in by counter rotating rolls, and when it comes out it is molten, and using this nozzle you are spreading the material over this platform. One by one layer is deposited, and this is quite economical process. Its resolution is low, but you have to deposit support material, correct? And later on you have to remove the support material. The surface quality is poor, the strength is also poor, but in this process you have the accuracy is reasonably good, the strength is reasonably good, choice of materials are too many, and there's no need of deposition of support material, because the unsintered powder, it acts like a support material in this case, correct? So then the latest development in the area of 3D printing is about laser engineered net shaping, correct? So this is a metal fabrication or metal 3D printing process. Here what is being done, that you have a conical channel, correct? And from this channel you are getting the various powders. The powder, this may be one powder, this may be second powder, so they mix, and the laser comes from the center, and basically this powder comes by suspended in some inert gas, and in this environment they gets melt, and you are able to deposit it on the platform. So this is called laser engineered net shaping process. It is also sometimes known as direct metal deposition, laser metal deposition, and direct energy deposition. There are various names given by various manufacturers. The different kinds of products which can be manufactured by this process have been shown here. Correct? So now let me talk about the applications. Correct? Now these 3D printing have variety of applications. They have applications in design, they have applications in manufacturing, analysis and planning. There are applications in biomedical application, correct? So one can make RP model, 3D printing model, and doctors can use it for some sort of planning and doing the mock surgery. Then you can make bioresorbable or maybe some different kinds of prostheses and implants using this 3D printing processes. There are a variety of manufacturing and tooling applications which I'll show you through pictures and which can be done using 3D printings. Geometry is never a problem, correct? So you can see some 3D printing products which have been manufactured by a variety of processes. So I'll not explain much because I have only few minutes left. So you can see the kind of geometrical complexity which is there. So in these situations, there's no other process which can be used other than 3D printing or additive manufacturing. So these are the distinctive features of 3D printing which makes it a very potential and suitable process in the environment of smart manufacturing, because you cannot make such things in case of using any other manufacturing process. Now you can see these metallic components. These are titanium medical grade alloy components. This is additive manufacturing in medical sector. This is made by electron beam additive manufacturing. This is made by SLM process. This is again made by electron beam additive manufacturing. So you can see that these kinds of components, they can only be done through additive manufacturing. This is a distinctive feature of additive manufacturing, which is actually makes it very potential process for Industry 4.0. Is another example of dental implant. There's some engineering applications. These are the arrow blades which can be done through these processes. These are some other very typical and complex components you can see here. This is called topologically optimized component. Again, a distinctive feature of additive manufacturing, which makes it popular for use in Industry 4.0. This is a typical die which has been manufactured directly through SLM process using additive manufacturing. Then let me talk about, so this is a headlamp. So this is a plastic component which has been painted by metal paint. So it improves the strength as well as surface quality. So that's how you can take care of stair-stepping effect. Now you can see this particular product, correct? The kind of intricacy it has, kind of good product it has. So you cannot make it by any other manufacturing process. So that's why additive manufacturing offers you good solution in a smart manufacturing domain. Now, in next generation of additive manufacturing, what we are talking about, that we are going to produce some smart components. What are these smart components? These smart components will include some sensors in it, and they will give you signals when the part is under operation, correct? So that's the kind of advanced components we're talking about, which may be a very good feature for smart manufacturing, that we can produce smart components which will let you know that, okay, now I'm going to fail after these many hours, correct? So you can take a preventive measure and there's no catastrophic failure, there's no stoppage of production or any machine in the industrial environment. So these are various distinctive features which makes it a very attractive process for Industry 4.0. So I think I'm stopping here. My time is coming to an end, and I have another lecture day after tomorrow. So I'll continue maybe with this topic, or there's some other thing which I'm supposed to speak on, maybe optimization or maybe something related to maybe how to stochastic processes, etc., that we can have for modeling or for arriving at a suitable decision in this Industry 4.0 environment. those things I will try to discuss based on the time and the limitation and what actually I know. I know things, but I'll not claim myself to be a great expert in the area of additive manufacturing because in the area of industry 4.0 because frankly speaking I have not done exactly so much of work which pertains directly in the domain but indirectly many small projects we have done like Professor Aviral was also my student. They have developed a lot of modeling work optimization he has done. So these are the tools which actually finally constitute the backbone or the for the development of smart manufacturing. So with these words, I am stopping, and I will meet you again on I think day after tomorrow. That is on 23rd. I'll meet. And if you have any question, we can discuss in 5 minutes. Correct?
Yes, sir.
Yeah.
Sir, there is one question that what is the difference between additive manufacturing and rapid prototyping?
Yeah, actually, I can tell you that in the beginning, it was said as rapid prototyping because it was only used as a prototyping tool. It was only used as a prototyping tool in the beginning, correct? And it was only used as a design tool. It was never used as a manufacturing tool. So slowly, as the capabilities of this process kept on building and people have developed variety of applications, different processes, many new materials were developed, and today we are in a position that we are printing even the metal components, correct? Metal components maybe of stainless steel, maybe some alloy steel, maybe super alloys, maybe titanium medical grade alloys. So in this scenario it becomes a rapid manufacturing and we named it as additive manufacturing. Now a desktop small machine which I can use even in my office is known as 3D printer, correct? So actually principle wise they are same, but a small version which I can use in my lab environment or office environment, that is known as a 3D printer. Okay, I think I have answered.
Yes,
Is there
sir.
any other question?
Sir, one question is that what are all the process involved in introducing and testing a new material in additive manufacturing?
What are all the process involved in introducing and testing a new material? Yeah, like now there are two things. Like in every system, you cannot use every material. Like in stereolithography, there's only a class of material which you can use. Correct? That is a photosensitive monomer you have to develop. But like SLS process or maybe SLM process, you can use a material if it is available in the form of free flowing powder. Is it okay? If it is available in the form of free flowing powder, you can use it, and you have to actually do some study. If you're introducing a new material, you have to do design of experiments, and you have to find out a set of processing window for a particular material for a particular process. So experimentation has to be done, and you have to devise a process window or optimum set of a process parameter for a particular requirement. That's what you are supposed to do. Yeah.
Yes. Yes, sir. So I think there's no more question. And
Okay. So
I think Jan sir has also joined us. So
इसके बाद I think Professor Prashant Jain is taking the session.
yes, sir. Yes, sir. Yes, sir.
Okay, that
morning,
is
sir.
great.
He's with us.
Namaskar, Jain sir. So good. So let me close, and we will meet on I think day after tomorrow, and I'll try that I can give you some hands-on on optimization. That is a very important tool for this smart manufacturing, because if you are dealing with huge data, then in order to take a proper decision, there are various algorithms which you have to learn and you have to probably use. So that kind of session I will try to plan for day after tomorrow. So thank you very much for your kind hearing, and all the best everybody. Thank you very much. I am closing the session now.
Yes, sir. Thank you, Pandey sir.
Okay, bye.
Thank you, sir. Dear participant, the Professor Jan is with us. He is going to take the next session on digital transformation in manufacturing. Professor Jan is presently an associate professor in PDPM Triple ITDM Jabalpur. He has done his PhD from IIT Delhi on the additive manufacturing area. His current area of interests are rapid prototyping and tooling, additive manufacturing, 3D printing, CNC machining, geometric modeling, CAD/CAM integration, computational geometry, nanotechnologies in additive manufacturing, incremental sheet metal forming, MATLAB programming, GUI interface in MATLAB. He has guided 4 PhDs and presently 5 are ongoing under him. He has published around 100 plus publication in various international journals and conferences of high repute. Total citation of these amount to around 1,000. He has done around 5 to 6 sponsored projects from the various funding agencies. Presently, Professor Jain is also the Dean of Student at Triple ITDM Jabalpur. Sir, we welcome you from on behalf of the organizing committee. Professor Jain.
Thank you, Dr. Aviral.
Yes. Thank you, sir, for your presence, sir. Accepting our invitation as a guest speaker.
Thank you, Dr. Mishra.
Sir, you can start your session, sir.
Okay.
Oh. Present. So your screen is visible now, sir.
Hello, my screen is visible to everyone?
Yes, sir. Yes, sir. It is visible, sir.
Okay, fine. So it's wonderful to talk to all of you after Professor Pandey's lecture. And we have already discussed a lot about Industry 4, smart manufacturing. So I will, in this session, will talk on some CNC machining, how we enhance the computational capabilities of CNC machines and take these machines for smart manufacturing, and how we can have more sensors, more electronics part to make it more automated, leading towards Industry 4. So let us begin with this, what we call is the digital transformation, right? We call it the process using digital technologies to create the new or modify the existing manufacturing facilities, business processes, culture, customer experiences to meet changing business and market requirements. So this what we reimagination of the manufacturing business in this digital age. We have come far beyond our keypad mobile phones. Now everybody use the smartphone, touch panels, and in our laptop, etc. we have a lot of new facilities. So this reimagining of the business and manufacturing in this digital age is the digital transformation. So when we use so many digital devices, being a mechanical engineer, it's a great challenge for all of us to collaborate with electronics and computer science fellows. We should enhance our knowledge and skill set in this challenging manufacturing environment, when we should have a good knowledge of programming, PLCs, various sensors, etc. And we should understand how other disciplines like electronics engineering or telecommunication or computer science and the design ergonomics parts is day by day improving. So that digital transformation is certainly required for manufacturing as well. Why? What the requirement we go? First thing, the enhance operational efficiency with improved processes. Then we must utilize this digital transformation to innovate by utilizing state of the art available technologies to nowadays. And our motto should be to attract and empower the next generation of workers. That time has gone when we should understand what the work to be done on the shop floor, the carpentry, the smithy, the heat treatment, etc. Still, these things are still required, but with lots of digital sensors, technologies are available to measure the temperature, to take the decisions on our behalf, and that will certainly increase the customer satisfaction. And finally, we our objective is to reduce the cost, right? So based on these requirements, we proceed with the digital transformation. So let us have a historical perspective how we have begun it. What you can see in this screen. Anybody could respond.
Yes, sir. Yes, sir. Hello.
Anybody can respond. What we can see on this screen? What is the design behind this screen? In the slide, we can see.
Water wheel.
Yes, correct one. The water wheel is there. Look at that. If we talk about more than 200 years ago, the product will be designed. And that design, everything revolves about the designer. What is the communication medium we talk about? Right? So that was the telling. If you design something, you have to construct something, and you are the sole person. There is no medium, no communication set available to transfer this knowledge to anybody else, to your team members, etc. Right? If I go back and then just talk about the 100 years ago, what has happened? Started the drawing board, the millions of engineers across the globe are able to collaborate with the same drawing language, right? So you look at that, the old offices, when we have the mini drafting machines, etc., and used to create a lot of drawings, orthographic views, manufacturing drawing with tolerances, etc. But what the difficulty in that? Every variant of the product requires a new drawing. So if we have this kind of drawing, and for a small variation, you see on this zoom portion, we require a new complete drawing, right? So the reproduction, copying, transferring is a challenge. Then we got but the advantage what we were getting with our 2D CAD packages, if you talk about the 20 years back, we have only the AutoCAD kind of thing, right? So it is very precise. Instead of human-made drawing sheets manually, we create so many drawing sheets. But in this case, it has become very precise and facilitate modifications, allow us to reuse the existing drawings, allow us to use the layers, blocks, etc. Right? So the 2D CAD has facilitated the transformation are in the drawing language. Then the system has further developed, and we had the 3D modeling. So we have lots of packages like Croi, CATIA, SolidWorks, UG, etc. to have any complex geometry and the assembly to be designed. See some of the examples you can have. Like you can see the detailed ribs in this, the different holes. And if we talk about the transformation of this drawing by just communicating a 2D image, it would be very difficult to transfer it to other design team members or manufacturing engineers. Okay, so how many orthographic or typical views are to be shared with our team member, right? So look at these, some of the typical components which require typical communication and design data exchange from design to manufacturing, right? So look at this various assemblies. Then we move from the assembly to the design analysis. So with the 3D, what we have developed so far makes us very easier. Still, we make a geometric model in CATIA or TOEI, and then we import it in some other format in the ANSYS or COMSOL or Abacus for engineering analysis, right? So you can see an engine block where all movement analysis can be performed. Right? This is how the digital transformation is taking place in the manufacturing as well, right? Then you look at that was not sufficient. So the digital mock-ups are required, right? And then optimized design for ergonomics and maintenance part has to be taken care. You can see a flight simulator is there. So what the portion we can see from a flight outside is how other devices would be working, whether they are in the range of capturing by our own hand or something like that. So all aspects of ergonomics and maintenance parts can be simulated in this, right? But after this also you see what it also requires the automation of the process. Let me come back to the automation. What we call the automation. If I go with a definition kind of thing, we will say as a trend of science and technology, which causes the process to be carried out fully or partly according to a previous set instructions, right? So human interventions will be minimized for automation. But look at this, whether this automation means fully automation, sensors everywhere, no, nothing like that. Automation, if we go for the characteristics point of view, what we have the essential characteristics for automation. We have one thing, ability to make decision. Means our automated system should capable to make some decision, right? And then making decision would not be sufficient only. So what is required? We need to convert this decision into a physical actions. Means if we decided something, our system decides something for your own behalf, then you need to change it to then you need to convert this into some form of actions, maybe machine switch on off or something else, right? And then finally we require ability to evaluate and control its own performance, right? So means whatever the system we use for automation purpose, it should evaluate. Means whatever the physical action has been done, whether it has been executed or not, and if it is executed to up to what accuracy or what precision level it has been executed, means it should have a feedback system, right? So based on these three characteristics, say for one example, let me take a example of a pressure cooker. What do we consider it? So can we say it is an automated device? Anybody? I would seek a response at this point.
Yes,
What we
yes,
consider?
sir. Yes, we can say. Yes, sir, we can say.
Right. Okay. So once we say the pressure cooker, what it does for us?
It cooks.
It cooks, but if we talk about this point, look at this, what it says. At certain pressure, it's not measure the temperature, it's measure the pressure, right? So at certain pressure, it decides that, okay, now pressure reaches up to its limit, right? And once it is decided the pressure reaches up to its limit, it has take some physical action. So the deadweight safety valve or whistle, we can say simply on the pressure cooker is lifted, right? So whatever the decision your pressure cooker has taken, that now pressure is gone beyond the limit, so that it has converted into a physical action, that whistle is lifted up, right? And then what happens once it is lifted up? The pressure releases, the steam come out of the pressure cooker. So as a result of the steam coming out of the pressure cooker, the pressure is coming down, right? And the pressure cooker is again evaluate its own control and its own performance. Means it can take decision, just not only releases the pressure, but it also check or recheck that now pressure is within the limit, right? So once pressure is within the limit, your whistle is getting down, right? That is the only way you take 3 whistle, 4 whistle or 5 whistle depending on the item what we are cooking in the pressure cooker, right? So we can define a system based on these essential characteristics. How much minimum human intervention is there and how much it is automated, right? That is the key for all industrial revolutions, whether it is a industry 1.0, industry 2.0, industry 3.0, and now in industry 4.0, what we are talking, right? The digital transformation all, right? Now question is this is a complete mechanical device, no electronic circuit, nothing is there. But still I say the pressure cooker is an automated device which makes some decisions, which convert these decisions into the physical actions, and it will continue to evaluate and control its own performance and again convert this into the decision followed by the physical action, right? So similar other devices we have the governor, no electronics, no circuit. Similarly, fly ball for water tap flow control. So we can have many such things which we call it automation, but now we have good electronic sensors as well. So we can simply making it mechanical only. We can also utilize the electronics and logic, Arduino boards, etc. for programming purposes and passing on the signals. Right. So this is the automation, the basis for all industrial revolutions, right? That has been transferred to the CNC machines. Look at them in early around 1970s, the CNC machines were come into picture. The design is like that. So very typical and not very good designs, we can say. We have the open here on the pallet changers are already available. The horizontal axis CNC machines are there. Then the designs were significantly grown up, right? So in the new designs are some modern designs are like that. The closed chamber for cooling, for coolant purposes, etc. The proper, you can see here, the digital keyboard is provided in this area so that you can enter, you can edit your part program, you can make lot of corrections, right? So this completely digit based, right? No manual lever or nothing is required on this milling machine, and similarly for other lathe machines, etc. So complete digitization in the manufacturing field has started with the invention of the CNC machines, right? In this session, we will talk about how we supply the digital information to the CNC machines, how the CNC machines read this information, right? So look at this. This is the part of the CNC machine. Then we require a lot of simulation. So again, we require a lot of digital technologies to allow us for the CNC simulations. Look at this. This is the software, you can say Dalcam or PowerCam or many other CATIA also provide the CNC machining simulation softwares. So we use a lot of this simulation before going for our digital CNC machines, where we provide all the instructions in a form of numerical or sometimes alphanumerical values, right? So that's the way we proceed with simulation, typical simulations for toolpath generations. Right, this is the toolpath simulation, right? Look at this. We go for this, the typical programming is required. Look at this and this, a lot of rotary machines on this lower left side to maintain the 5 axis and the mounting of the workpiece on the CNC machine, right? And then we require a lot of, say, for example, this turbine blade machining is going on. So for further improvement of our CNC machines, we require a lot of computational facilities, and not only the computational facilities, these computations has to be transformed in the hardware. So we require a lot of control of ball screws, etc. And to make this 5 axis machining, look at this video. That workpiece is mounted on a rotary table, so two rotary axes is in the work table itself. Let me run this video again. Right, so this is the few examples for 5-axis machining, right? And these are the rotary tables we can have. So in both x-axis and y-axis, we can rotate these tables on horizontal machining centers to achieve this 5-axis machines. So here the lot of modernization, digitization is required for the future CNC machines, where now people are using more than 20-axis machines on the same machine, and a multiple axis is also divided based on the unit system. For fast traverse, we use the x-axis, and on the same axis, just like vernier scale, we have a 2 scale, right? So one normal scale and then vernier scale for measurement on the same direction. Similarly, for CNC machining axis, we also use more than 2 axis control system, for one for small traverses and one for large traverses. Right, so with this rotary tables, you can see another example of this rotary table. The vertical machining center is there and the workpiece mounted on this table. Right, so with this servo control, we can rotate this table itself to reach out the workpiece desired point, maintaining this tool perpendicular to the workpiece. See this example, why we require this. Look at this rotary table. Here we can mount this workpiece, right? And the tool is every time coming straight from the Z axis, right? So we can rotate the workpiece to maintain that every time the contact point of the tool should be perpendicular to the workpiece to maintain this surface. If we do not maintain, look at this for freeform surface machining on this figure. This is the tool, every time it is vertical. And if we do machining in this direction, right? Look at this. If we take it in this direction, the machining, right? Every time. What will happen? After machining, we may see the stair steps. In the entire this screen, the stair steps would become, right? So look at this. What is required on this screen, you can see. Every time my tool should be perpendicular to this cylindrical surface. This is how this is achieved. You see on this previous slide. The workpiece is mounted on this rotary table and every time tool is coming from the top, right? So by this way, we maintain that tool should be perpendicular to the workpiece for fabricate. This is a very, very simple example for, say, cylindrical. But look at that. Suppose, for example, you are making a die for your mouse, right? So you can see the surface of mouse, how typical it is. And for making die, every time your tool should be perpendicular to your mouse die. Look at this. This also require when we convert this into a part program. So before going into the part program, we require a lot of calculations, right? So we need so many programming to be done. Say for example, this here, this is the blend and we need to this cut. So for first cut, this would be the cut. Second cut, this line, the tool will follow this line. Third cut, tool will follow this line. And subsequently for all cuts. This you can say the finishing allows, right? So this is the one case when the cut is parallel to the axis of revolution, that is Z axis for a CNC lathe machine. Look at this. This might be tapered cut also. For a taper cut, again, you see this profile needs to be offsetted. So we should know how to do the program to find out or take this profile offset, right? Now look at this again. This has to intersection to be calculated to find out this point. Then tool will go back, then come back again on this point, this point, this point. So all these intersection points to be calculated, and then accordingly we need to develop a tool path. You can see this is a datum, right? Look at this. Say for example, this is the workpiece to be fabricated on a CNC lathe machine. So how we develop this CNC program? I hope all are aware about the part programs. Any response?
Yes, sir. Most of the participants are faculties. I think they must be aware with the part program.
Okay, so thank you, Dr. Naren. So I will take it about the brief of the part programming as well. But look at this. For such kind of CNC part fabrication, we require a lot of calculations before going into the part programming, right? So for example, just like in the previous slide, we have seen this is the part to be made. So you see, this is the X and this is the datum Z axis. So we plan this would be my first cut. Right, this would be the second cut, this would be the third cut, fourth cut, fifth cut, and this is the finishing allowance I have taken. So at the end of the material removal in the 1 to 5th cut, the 6th cut would be in a continuous mode, exactly following the tool profile, right? So this is how we develop the part program. But for this, you see, we need to calculate all these lengths. And after calculation of these lengths, we should convert this into the coordinate system. Based on that coordinate system only, we can convert this into the part program, right? Look at this, the same figure we have here. All cuts are there, but now we have to write for first cut, right? Starting from this, the Z0, X 17.75, moving in this. So axis remains same. Z value is minus 33.5 because we always take this as a 0, 0. This Z is positive. This X is positive, right? So the diametral programming is there. So we consider this diameter. This side Z is positive and this side Z is negative. So for first cut, this one. For first cut, you look at this, starting from this point, material removal takes place up to this point, then going back. So see on this point, Z is remain same, the X is increased, and then tool is coming back to here. This is for second cut, right? So when we start for the second cut, what will happen? It will move like this, right? So it is reaches up to 15.75 minus 27.5, right? You can see over here, our first cut length is higher than the second cut. For second cut, third cut and fourth cut, the length of the cut is remain same. So look at this, second cut, third cut, fourth cut. Our coordinates are, Z coordinates are remain same. The coordinate varies only in the X direction, right? So similarly for this last cut. And then we have to take this final cut. For this final cut as well, we have, like, our tool will start from here, continuously follow this. So we have to put linear interpolation, circular interpolation in all the place. So this much material we remove. Remember, we have not yet written any part program, right? We have just preparing or developing or collecting all the coordinate geometrical information before going for the part program. Look at this, another example. Suppose we have this kind of geometry, right? This cut to be taken, right? So what would be happen? This workpiece outer has to be the profile milling to be done in this, right? In triangular shape. So what would be my tool path? This red color, right? So what we can do, we can plot this in a SolidWorks or CATIA. We can apply the offset command, and from this triangle, blue color triangle, we can get a red color triangle, right? With this red color triangle, we can get these coordinates, right, from using the software. And then we can also write the part program, right? But sometimes it is not sufficient to use this kind of high-end software. So we should use our geometric calculations. We can also solve the equations on various geometries. Say, for example, this point is P1, right? So this point is P1 and we know this X is 4, Y is 4, Z is 0, right? But what we require, we want this point, right? So for this point, and the tool diameter is already given to us, 0.5. So we can, by radius, we can move it in this direction. So X is here, the 4. right? We can minus it 0.25. The new x for the tool path, the new x would be 3.75. The geometry x is 4, but for the tool path, this x is 3.75. Similarly, for y, we can solve this. We can make a triangle over here, and we can solve this trigonometrical equations in this way. Look at this here, and then we can find it out this point. So what would be the P1 is 3.75, 3.396 for y based on this trigonometrical equations, right? Mentioned here, 4.25 into 10, 67.5. So that's the value. So this kind of calculation needs to be done. We still need a lot of software, lot of programming routines to be developed to facilitate our CNC machines for such kind of operation. Right now we need to write the part program. So that calculation part is on our hand, right? See another example. Cutter diameter, the remains same. See for this circle point. This red color tool path is going on. So we need to calculate this point. We need to start the circular interpolation on this part and then move ahead, right? To make this kind of cut, semicircular cut on this tool, right? Look at this. So we need to formulate. You can clearly identify this is the equation of a circle, and the circle radius is already given in this diagram, 0.75, y dash is 0.25 because this has come from the diameter, right? And then we transfer all these coordinates. So this is the value we can calculate here for x, y, right? In the center of this circle is already we have 6.5 and 9, right? So based on this, we will calculate this point P3, then go for circular interpolation, coming back to this point and moving for further machining, right? So by this process, you can see we need to calculate all the points to define this red color tool path, right? Red color is the tool path, and this inner, the blue color is the geometry, right? So this is the way for calculation, and we need lot of utilities for this, right? This is one example for CNC. Once we calculation done, we need to develop the NC program, and then NC program is nothing but it is the alphanumeric coding of all geometrical points, right? It is not like our while loop or do loop or for loop kind of programming, right? So we mention here the sequence number N10, F60 means the feed rate, the spindle speed, and then other M codes. So this is G01, the linear interpolation. We started like this: X 3.75, Y 3.396. Then we move to the second point P2, Y 9.25. So X's remain same. Similarly, we keep on. When we reach to this circular interpolation, we were on this point, right? And then moving to this point, we go for the circular interpolation. So we have like this: the center IJ and the radius 0.75, right? So this is the center of the circle and the radius from IJ. So this is the start point, this is the end point for this semicircular. Okay. So this is the way the center of the circle. Look at this. Once we create this, we can convert this into the G&M code program. I have already shown in the previous slide. So right now there is no standard language available. We can have a controllers, the head and hand, Siemens and Fanuc controller, but the programming is still have a much difference in all different controllers. Different CNC machine manufacturers, suppliers, some use Fanuc, some use head and Siemens, etc. So they have their different or little bit difference in the G&M codes, right? But in a general or very generic way, we can say this contains the NC word. So these are the various NC words, and a combination of NC words we call it block or command. So when we say block or command, means one single command which can be executed. Means say for this line we have the sequence number, We have the interpolation, whether it is a rapid interpolation, rapid traverse, or linear interpolation or circular. Then it is the coordinate system on where to leave, right? And then it is the spindle switch on. We can also maybe the previous line or in the same line we can add the feed rate, etc., the spindle speed, etc. So right, the block is a group of NC words which can be executed on the CNC machine, right? So this is composed of various letters X, Y, Z, R, and many other letters. We will come into later. Look at this. If we go for a G code, so we have the various words like N, G, X, Y, Z, ABC axis, I, J, K, then feed rate, F, S, T, radius, miscellaneous code, etc. Right? So if we say N is the sequence number, if we talk about the G code, the proprietary word that will keep the machine ready. So G00 is the rapid movement, G01 linear interpolation, G02 clockwise interpolation, G03 anti-clockwise interpolation, then turn off cutter compensation, right, etc. Then F will define the feed speed. So this is again depend on what the unit we have considered. It may be inch per minute, it may be inch per revolutions, IPR also, right? See, if we convert this into a part program, how my first part program will look to me, right? Look at this. This would be the part program. So suppose I am mentioning G71, G97, G94. I'm defining my machine settings. So my machine settings would be in a millimeter mode, that the constant RPM, then feed in millimeter per minute, right? Then I say G28U0W0. So this is go to home position. Then I say M065. So I'm giving instructions to the CNC machines for tool change, and the tool number would be T5. So my automatic tool changer will take go to the tool changer device and select the tool number 5 and come back to the workpiece. Then when I say M03S1200, right? So it will say the clockwise RPM would be there and with the 1200 RPM, right? So then the coolant on, then G00X42Z1, it will take up here somewhere. So tool will start somewhere from here and it will reach to here. This is my datum, right? And then we G01Z minus 50. So the first cut would be occur like this, right? Then we go back the tool path up to the previous position and in the second cut, right? So this will be the second cut, right? Since it is a revolutionary part on the lathe machine, so on both sides you can see the cut because the workpiece would be rotating on the lathe machine spindle, right? So this is the first part program we can say with a linear interpolation. And when I say the M05, so spindle on, M09, the coolant off, the M30, the program stop and rewind. So that is my first CNC part program. Look at this. If we take it to the circular interpolation, remaining things are same. Only thing, instead of G01, now we are putting G03, right? And giving the radius value. So how it will work? It will work like this: the first, second cut, third cut, like that in a circular fashion, right? You see, this time, suppose I have instead of aluminium, suppose I have written a program for aluminium machining, right? And I can take maximum cut on a good heavy duty CNC machine, say 5 millimeter. But now suppose I have been given a titanium. I can't go with 5 millimeter cut. I may all of a sudden require 0.1 millimeter cut. So I may need to write thousands of lines in my part program, right? So in those situations, we use the canned cycles, right? So what is the canned cycle? It's a predefined machine instructions, which are permanently stored on the machine controller, and we can initiate them as a single G code, and the multiple operations will be calculated on the machine itself. Right now, machine have this capability to calculate these multiple runs of a tool, but this combination should have only either the linear geometry, either the circular. No other like synthetic forms we cannot use, like our Bezier curve, or spline, or B-spline, or nerves, or anything else of higher order curves, right? Only the circular and only the linear. And even for circular as well, machine will subdivide into a small linear segments. So we may sometimes lost the accuracy. What we desired the part to be fabricate, our part may deviate from that. So look at this. There might be 1,000 of lines in this simple program, right? But here when we say this is a CAN cycle, right? So the lot of calculation need to be done. Okay. So what we have done in this CAN cycle, let us very briefly understand. We define in a few lines the depth of cut required, right? Here we define the block number, means from where the CAN cycle is start and up to where the class CAN cycle is going, right? So start and end. Then here, because of this block, we have given Q120. So this is another sequence number Q120. So here the CAN cycle will stop, right? Then we have a retract height, means how much we have to take the tool upward direction. Then we have some finishing allowance U that will give the finishing allowance in X direction. W will give the finishing allowance in Z direction. So the entire geometry would be offsetted. Then the cutting will take place parallel to the Z axis or parallel to the X axis or parallel maybe by offsetting the profile as well. 3 different CAN cycles are there. And then we also provide some finishing allowance, right? So based on this, the CAN cycle will work. Let us see how the CAN cycle works. Suppose this is the profile, right? So this profile will be offsetted based on the finishing allowance. Based on this finishing allowance, we will start calculating these parallel tool paths, right? And the machine will work like this. The first it will tool will go down in the X direction, then it will cut the material. Then this is the retract height, right? Whatever the retract height we will give, tool will be lifted from the workpiece and go back. Then the next cut it will come out, right? The next cut will go like this, right? Look at this. So it is not touching the actual geometry, actual desired geometry. Because of that, we have already applied some finishing allowance in this multiple turning cycle, right? So this is only take the turning operation, right? Now with this, you see when it reaches to this point. Look at this. When it reaches to the last point, it will follow this point, right? So what will happen? Whatever the steps created in this previous machining, because tool has come here, gone back. And earlier step, tool has come over here. So the small stair step would be there. All these stair steps would be removed by this CAN cycle, right? So here we can take a 5-minute break, or if you have some queries, we can address here. Then we will talk further how to enhance the computational facility for CNC machines, and I will show you some MATLAB programs which we have developed to machine the Bezier curves, right? And we can also simplify the CAN cycle. Some of the machines may not have the facility of CAN cycle, so we can also develop this computational facility for very low-end machines and can improve their computational facility as well. So if you have any question, let me stop sharing for 2-3 minutes. If any question at this moment, we can take a few questions. Yeah, from the participant side, if there is any query.
Yes, sir. Let me check the chat box.
Yeah, please. 1 or 2 minutes.
Sir, there is one question from Satish Kumar. He is asking how to select the correct machining parameters for a material to achieve desired surface finish in CNC machine. Sir, he is asking about the correct machining parameters.
Right. Is my screen visible now?
Yes, sir. Yes, sir. But yeah, simplification of CAD cycle.
Right, right. So regarding machining process parameters, we have to select the material and we look for the material removal rate and the heat generation. So that will depend on many other parameters like whether you are using the coolant or not, and how much heat is generated on your machining system, how much tool nose radius you are taking, whether the edge is sufficiently sharp to cut the material. If your tool become blunt, then some built up edges will be formed. So even though while machining your surface would be very smooth, but because of the built up edge, some chips will again welded with the workpiece, and when you try to remove it, they will deteriorate your surface finish. So that is what we do, lot of experimentation, design of experiments to identify the suitable process parameter which depend on the material as well. Sometimes the material may also have some impurity where the hardness of the material might be varying across the bar which you are machining. So these are the means, there is no such kind of thing like you can select this. Lot of design data books are available depending on your tool nose radius, machine power available, then diameter, then speed. Say for example, some situation you may come across where the taper machining to be done on a lathe machine. So when you have the taper where the diameter is less, your cutting speed would be changing with the change in the diameter. If you have reached to the higher diameter, the linear speed would be higher in that side. When you have the smaller diameter, your linear speed will be less. So even on the same workpiece, in a taper machining, your surface finish may vary. So you have to go for the such kind of corrections you have to take care while machining. Right. So a lot of research work is going on in this area, and almost many parameters are well known in a design data book. They are available what you are going to take. Only thing you have to make some corrections. Say for your tool has become bold, blunt, and how much tool life you have already adjusted, right?
Sir, another question from Vikrant Sharma. He is asking about the usefulness of CNC, whether NC are useful in industry today or not.
Okay.
NC, not CNC, NC are useful in industry today or not?
This is what the difference we take. We take the numerical control and computer numerical control, and if you remember, we also study in books like DNC, direct numerical control, yeah, distributed numerical control, right? So we have NC, CNC, and DNC. Numerical control machine is also nowadays, because this has happened when 1970 the development of CNC machines have come into picture. What happened? The cost of the computer system is very high. People can't afford a system by their own. So we have a big workstation kind of thing from where we distribute the instructions to different CNC machines. Right. So based on these instructions, we try to use that computer facility, one computer facility for all the machines, right? So we have a lot of LAN networking, RS-232 cable port networking to distribute the instructions, right? In the day by day, what happens? The computational cost and the computer system cost has decreased a lot, right? So that's why now you see everybody is carrying the laptop, etc., and we have a good memory like 8 GB, 16 GB, 32 GB in our laptops, good graphics cards, etc. So if you talk about the NC, you can still have. And in the CNC, we provide one single dedicated computational facility on the machines. But if you go to the large factories like we visit regularly in Jabalpur, the vehicle factory, the gun carriage factory, the gray iron factory, they have a lot of CNC machines. So for data transfer, part program transfer, we still require networking and connection between all the machines. Right. So nowadays we do not find much difference in NC, CNC, and DNC. Every machine can have its own dedicated computer system but still they can be connected through the LAN for data transfer purposes, instructions purposes like this. Earlier, what happens in my stage when I did my BTech, I remember there is no dedicated RAM available on the CNC machines. We used to that the floppy disk of 5.4 inch floppy disk, the big size floppy disk. One floppy disk we use on the CNC machine to load the operating system. Then we remove that floppy disk and put another floppy disk to load the part program. That was the level of the computational facility, memory and RAM, etc. availability on the CNC machine. So in those days, we were depend on the LAN networking, etc. Nowadays, computational facility is so easily and so economically available. We now in industry we use the CNC plus DNC, a hybrid kind of model, right?
Sir, another question is from Satish Kumar. Is there any type of CAN cycle used in CNC machining center?
Yes. Okay. Let me proceed further, and I will take up this CAN cycle again in a little bit more detail. What we have already started. So I have added few more slides to discuss more on the CAN cycle and developing new CAN cycle. So now in my further slide, I would discuss two things. The simplification of CAN cycles means the low cost machines which don't have the facility of a CAN cycle, right? So what will happen? We require a lot of human efforts, lot of calculations to write the part programs, right? So and in another case we will talk. We will have another thing where the machine, even the new modern machines, don't have which we do not have the facility to machine the Bezier curves, B-spline, etc. So we develop new computational facility and convert them into a form of a CAN cycle, right? So let us see the simplification of CAN cycle. What is CAN cycle, right? So our motivation for this, the modern machines are equipped with microprocessor, controller, and a lot of computational facility, which make them to run the CAN cycle and subroutines. But very low-cost machines, economic machines, they don't have facility for a CAN cycle, right? So these machines can still machine the complex shapes by performing basis operations, thus like linear interpolation, only linear interpolation, or some cases circular interpolation, right? So in this case, the program may be too lengthy and may cause inconvenience in program writing for the programmer. So we have developed a software utility to convert a simple part program into the CAN cycle, right? So what will happen? We will develop a part program using a CAN cycle. So we need to write only 10, 12 lines or just to define the geometry, right? And my software utility will convert this into a linear program. So that linear program may contain 1,000 lines. So I will upload that on the machine, that 1,000-line part program, but manually I will not write those 1,000 lines, right? So look at this. Say for example, single facing cycle. What the single facing CAN cycle will contain? If I do not use a CAN cycle, what I need to write? I need to write this movement, this movement, this movement, and this movement. So if I talk about the single facing cycle, I need to write 4 movements. But if I use the cycle, I can write only 1 movement, and then the 4 operations will be performed by the machine. So that is 1 cycle, right? If we take about this, similarly, in this case also, sorry, there is a typo. It's a single facing cycle. So once we go with the facing cycle, all these 4 movements, the black dot is showing the cutting movement, red dots are ideal movement, non-cutting movement, right? So look at this. What we do, we will take this tool in this direction, right? Without cutting, it will go into down and will come. Right? So this is the point. right? And then we have the multiple turning cycle. So what we do in this multiple turning cycle, our tool will start from here, right? Coming back, then cut, then coming back, then cut, then coming back. Okay, so then how we cut the part. Look at this, tool will go down, cut this material up to here, revert back and go back. Similarly in the second cut, right? If we write all these operations without using canned cycle, we need to calculate all these points, red dot and this. Right? And then what we do, we define in this canned cycle only this geometry. Right? Look at this, how this canned cycle will look like. This is in the facing cycle. Let me check. Where is the canned cycle? Right? We talked here on the canned cycle. Right? Somebody's asked. Right? So what we do here, we define the geometry in a linear interpolation, circular interpolation, right? All lines would be there and all geometry points are there, whatever the coordinate of this geometry to make this taper. Sound is right. So look at this. In this, after this canned cycle, what do we do? Sorry, let me reach back to the same position. So finishing cycle, right? This one. We define in the canned cycle only this geometry, right? Okay. Look at this, for facing cycle, we will define movement in this direction, right? Perpendicular to the axis of revolutions, but we do not require to calculate all these points. And now if you look at this, if retract value is less, our depth of cut is very less, then what will happen? This number of these lines or number of cuts required would be much higher, right? So look at this, if we have a pattern repeating cycle, somebody was asking, so 3 types of cycle we use. Multiple turning cycle, the cutting would be done parallel to the axis of revolution. Then multiple facing cycle, the cutting would be done perpendicular to the axis of revolutions, right? And then we have this pattern repeating cycle, right? So every time my tool will move parallel to the pattern, means whatever the desired geometry, right? So instead of, it would be neither parallel to the axis of revolution, not perpendicular to the axis of revolutions. And then, okay, look at this one case study when we have developed a canned cycle for operation, right? So this is the part geometry I have selected, and in 3 operations, what we take this cut, second we take this cut, third we take this cut. So 3 canned cycles we have utilized here to fabricate this part, right? While we do this fabricate, our objective was this. This is the concept on 250 MCO machine. This is the MCL2 Envirotech indigenous machine design only for linear interpolation, right? So there is no canned cycle available on this machine, and on this machine we have the facility of the canned cycle. What we wanted, we should write a program on this machine, but that program should be run on this machine. which do not possess the capability of running the Kent cycle, right? So for this reason, what we did, we develop a program on this Kent cycle. This is the program developed with the Kent cycle. Now, the developed utility find out this geometry, draw some horizontal lines, calculate the intersection points, and add some points to take it lift upward direction and going back. So instead of once we calculate one intersection point, then we apply suffix prefix of the points, and this program be generated. So look at this. This program belongs to, if we talk about the sequence number, only 32 lines, and these programs have 140 lines. And if we if we decrease the depth of cut, these lines would keep on increasing, right? So this is the part program with Kent cycle, and that is the simplified part program without the Kent cycle. This is the simulation we check on the MCO machine, right? So manually we write this program. The software utility will give me this program, right? Once we simplify this program, what will happen? We can check it. If we have a depth of cut, just to understand the advantage, depth of cut, what will happen? For 2 millimeter, the cycles, the number of lines in the Kent cycle is 27, and the number of lines in the simplified part program is 83, right? But if we keep on decreasing the depth of cut, you see here, when we reaches to 0.1, to define the geometry, we need 130 lines, but it will reach to 1219 lines. So that utility will save our time in writing the part program. And we can provide this computational intelligence to even our economic or low cost CNC machines as well. Even though right now our machines does not have the capability to, okay, so let me skip few slides. This we can also do for the milling operations, Okuma milling and Amco milling, and some drilling operations. So let me skip. This can be converted into the part program, and we can remove so this one part program without the Kent cycle, and this is the simplified part program without Kent cycle. So the number of lines would be increased, but this can also run on any of the machine, right? So we can compare. Okay, so I hope I have answered about the Kent cycle. Basically 3-4 types of Kent cycles available on the CNC machines, and the purpose of Kent cycle to reduce the programming efforts, required for programming, right? Right. So now we talk on the enhanced computational facility for CNC machines. Say for example, CNC machine does not have the capability to machine the Bezier surface, right? So let us see. Our motivation is this: to equip with the microprocessor computational facilities capable to run Kent cycle, but still these routines are not developed for free for curves. So we need to develop further subroutines and Kent cycles for the for this high-end curves, synthetic curves like Bezier, B-spline, nulls, etc. So look at this. Those who are aware about this Bezier curve theory, they can see these are the synthetic curve, need not to pass through the data points, and we can have, right, continuous curves. Right, so there are so many equations to calculate the Bezier curves, and it can be n number of points, and it can be a nth degree curve. So maybe the 20-25 degree curve for large curves we can have. Then vertices are numbered from, okay, leave it, this one. So what we do, suppose this is the Bezier curve, right? And if we want to take the cut in parallel to z-axis, we draw the horizontal line, and here they calculate the intersection of one single line with one then all these intersection points we calculate, we record, and if we take this parallel to x-axis, we draw the vertical lines, right? And we again calculate all these intersection points, right? So this is the Bezier curve and intersection point. Based on these curves, we again write a Kent cycle, right? What is that can cycle? We write so once we write this N10 N10 N11 20 T0202 like this, so tool number N30 G00 X45 Z2, right? And now here you see this is the new number of the can cycle given G79, right? So this is the depth of cut 0.5, this is the retract value 0.2, and this is the number of points to be calculated on a Bezier curve, right, for accuracy. So we can keep it 110 or anything like that, right? Then this is the start for the contour, this is the end for the contour, and this is the offset for finishing allowances. Okay, these are the points up to, say for example, up to 110. So these are the points are for right, these are the points for the to define the control polygon of a Bezier curve, right? So based on this control polygon, this software utility will calculate the Bezier curve, calculate the intersection with horizontal or vertical line depending on the requirement. Then it will develop the part program, right? And it may be a thousand of lines of the part program, right? So start of the can cycle, depth of cut, this is the retract height. These are the linear segment, right? Then we have block number means P60. So your geometry is starting from 60. Then we have end. So up to 110, you have announced that up to 110, these are the control polygon points, right? And then we have this U2 finishing allowance in X direction, W1 finishing allowance in Z direction, right? So since you have given 10, here the can cycle is over. Then again you have G72 for finishing cycle. So we redefine this geometry so that finishing run would be taken in a single cut, right? Then we close the program. Look at this, based on that we have developed a MATLAB program and a utility. So user need not to do much, only he can select the some points for Bezier curve, right? Some computational intelligence also provided learning cycles we can take up, right? So let me run the program. Here we can see the simulation. We can also see how the part would look like after this program be run on the CNC machine, and with some computational intelligence like identification of the cusp height. Look at this, if I draw the Bezier curve in this way, right? And every time my tool has to come from the parallel to Z axis. So to reach out this point, what will happen? The tool will start from this point. And when tool will start from this point up to this point, what will happen? This much material will be removed, which we do not want to remove in this equation, right? So in this case, pattern repeating cycle would be okay, but to avoid this undercut, we have a computational intelligence provided to the machine itself. So machine will tell you that okay, if you proceed with this part program in this way, there would be a undercut, right? So before I run, let me talk about a little bit more what the challenges we face in this kind of digital transformation, right? What we have, the first thing is the employee pushback. People are the workers or operators of the machine may not like to have this new technologies to happen. If you look it into that, the old people, even including us, ourselves, old teachers, they still want to try tell us whatever they learned at their own age, right? So people do not want to adopt the new changes. That would be the first employee pushback would be there. Then again, the lack of expertise to lead this digitization initiative. For example, I am talking about the Bezier surface machining. Many of us are not aware about the Bezier machining. Then second thing, many of us may not be good in the programming in Java, Python or MATLAB. Then converting this in the utilization GUI form, utility form. even though we done, then some of may would not like to go for the Arduino board programming, develop new circuits and new machines, right? So these are the challenges we face because of the expertise not available. So the curriculum needs to be revised in that way. Our BTech, our diploma, our ITI level fellows should be trained accordingly so that they can deal with the new environment of manufacturing. Then another challenge will come from organization structure. Then the overall digitization strategy. Only providing a good CNC machines may not solve the purpose. You require a lot of business model planning is also there. So if you buy a high-end CNC machines, you can't use that machine for a 4-hour working in a day. You should try to work on that machine in a 3 shift in a day, so that the full utilization can be done and your break even and a point should be as low as much possible, so you can quickly recover the cost. Then the supply chain has to be improved, the order chain has to be maintained to have such kind of, so that digitization not only in a manufacturing but in a business strategy, order receiving, everywhere this digitization has to take place, right? And then finally the always as usual the budget is requirement, right? So that has to be taken care by everybody in the management level, and the justification and return company should have by making this kind of digitization. But I must say that is nowadays is must to be remain in the manufacturing world and remain competitive for this. So I would say thanks with this, but before this let me run a MATLAB program as well before I conclude this to show you the last. In the meantime, if we have any queries, we can now take up the queries. Or else let me run this program. Just look at this, the what program I have shown you. All right, the same program I am running. Look at this. This is the utility we have created. We can select some points in this Bezier in this one. Right? When we say the Bezier curve is drawn. Right? It's not circle. We can set the datum for machine programming. So this point will become 0, 0. Right? This is the datum. Look at this. This is 0. This is on this side also 0. So if I go for turning cycle, it will ask me all the process parameters, say for depth of cut, retract height, finishing offset in Z direction, and finishing required or not required, right? So let it go with the default values, right? And you see, this is the simulation for toolpath. This intersection points, it has been calculated by drawing these horizontal lines on this intersection point. Then these points are added to this. So that's the simulation we can see. Like not only this, we can see the part, how the part look like after the machining. Look at this. This is not a circular interpolation, and we can rotate and you can see on this. This is not a commercial package. Like this is just a simple program, graphical user interface developed in the MATLAB. So by this we can have the simulation. We can generate the Bezier program, right? So this will generate all these coordinates. This can also generate the part program. We need not to write the part program for this again, right? So we can write the G&M code program from here itself. So just like other commercial packages, it will ask me to give this. So let me put NIPJ. And look at this, in this working directory, there is no such program exists. Once we go for NITJ and save the file, it will create a file in the working directory. Let us find out. Look at this, this NITJ file has been generated. If I go for open to you, look at this. This is the part program has been developed here, and this program we have tested on our CNC machine. We can directly load this program on the CNC machine, right? And this will give me the Bezier interpolation, right? So G72 code we have talked about, right? So this is all being converted into the G01, G00 like this, right? So that's the objective here. And this will take. And if I run it again, you can see, and sorry, let's close this first. Even if I take a cusp, right? So let me take a Bezier curve. Okay, draw the Bezier curve. Oh, sorry, there is no cusp in that case. So let me run and then rerun this program. Right, you can see the very sculptured part we can have. Look at this. Right, and if we go for the cusp height, you can see also want to store this program. See, this time we have a small cusp over here, right? And when we set the datum and when we try to give the process parameter, it is saying cusp found in the curve turning is not possible, right? This is the area where we found the cusp. It is mentioning it. This is the portion of the cusp. So this is how it takes the decision that cusp is found, turning cycle is not possible, right? So let me go back. That is what we have discussed in this session, right? Challenges, and I would say thanks to all of you. Yeah, Dr. Narendra, Dr. Aviral.
Yes, sir, I am here. Sir, okay. So let me check the chat box if is there any query or not.
Please.
Okay, so yes, sir. Another question from Satish Kumar.
Yeah.
And cycle. Sir, is there any option available in software or SolidWorks for CAD cycle generation?
No. CAD cycle, they SolidWorks, CATIA, etc. They do not provide any CAD cycle. They generate the 1,000 line or maybe 2,000 line program without the CAD cycle. So that just like Delcam, PowerCam, we can run on the CNC machines. CAD cycle mostly we provide, the machine manufacturer provide for manual part program writing. If we are generating a part program already from SolidWorks or any other package, there is no need for CAD cycle.
Okay, sir. Next question is from Mayank Agrawal, that can you think of any solution for this problem of crust formation?
Cusp, okay, because the cusp is there because you wanted that geometry. Geometry is so sculptured, there is a cusp already there. So your tool cannot move parallel to x-axis or perpendicular to x-axis, right? Rate of revolution. So in that case, we have to apply the third cycle, which is known as pattern repeating, right? So in pattern repeating cycle, what will happen? The length of the cut, total cut, if you calculate, would be much higher. But in such case of when their cusp is already there, so we have to follow the pattern repeating cycle. Means whatever the turn on your profile, your tool should also be follow that pattern, right? Your tool should be offsetted like that. That is the only possibility with that Kent cycle. With the
Yes, sir. So I think there are no more participants. Please, if you have any queries, you can post it on chat box.
yeah, we will have another opportunity to interact with all.
Yes, sir.
Tomorrow.
Yes, sir. Yes, sir.
So
Yes, sir.
any leftover questions for today, we will take up on the day after tomorrow.
So one question is there. Which software is available for a student to do and learn those simulations?
Just for simulation purpose, many open source software are also available because PowerMel, Delcam, these are the licensed software and very costly. So CNC simulators, etc. are available. What I have shown here, this is an indigenous developed MATLAB program. What I recommend to all the students to learn the programming, because the programming will give you an upper edge and will give you to operate CNC machines, logical thinking, and develop your own utilities. So
Yes,
that
sir.
is the MATLAB program, right?
Yes, sir. Dear participant, actually, Jan sir has indigenously produced this MATLAB codes in his lab only, and he is presenting us to learn something. I think this can be an opportunity for everyone to move in this direction. Maybe you can adopt Python as a language to code this. We will definitely appreciate Jan sir for sharing his research work. Thank you, Jan sir. Uh, uh, we from the organizing committee are very thankful for you to present this session in front of the participants. We are actually eagerly waiting for your next session, that is day after tomorrow, and participant will join you. Thank you, sir. Thanks a lot, sir.
Thank you, Dr. Avila. Thank you, everybody. Thank you, Dr. Naren. Good day.
Thank you. Thank you, sir. Same, sir. Dear participant, we will meet again at 2:30 with the session from Professor Pradeep Kumar. Till then, you can have your lunch and we will meet again. Thank you all.
Okay, no problem.
So, good afternoon, participants. I welcome you again in the post-lunch session of this STC. So, so in this session, Professor Pradeep Kumar will be taking about quality function deployment. Now I invite sir to deliver his talk. So, sir, please, you can start, sir.
Can you see my slides?
No, sir, अभी तो नहीं.
Yes, sir. Yes, sir.
उधर आ गया? हाँ, yes, sir. आ गया.
आ गया, ठीक है. So I'm continuing, right?
Okay.
Just make it sure that you switch off your individual microphones, no? So a lot of noise is coming.
Yes, sir. Yes, sir.
Okay, good afternoon, everyone. And thank you very much for giving me this opportunity. Today, my lecture is on quality function deployment. You can see this slide and this picture also. So if you see this picture, there is one swing on the basically a tree that normally we use for just swinging action. And since it is already this month, that is the Shravan month, many ladies basically use this also. So what happens when a customer asks, because direct contact between customer and the company is the marketing personals. So when marketing persons approaches a customer, so he has in his mind that he wants a swing. So he explains to the marketing people. He don't have the picture, but he explains. So he explains that I want something using that I can swing basically. It can be tied on the tree. It should be very sturdy. Safety should be there. 2 or 3 people can also swing together. So he explained to the marketing persons. So if you see the first one, it says what the customer wanted. Customer was trying to explain that I want a swing that can be hanged over on the tree and he can swing, he or she can swing. So when the person who is in contact, he understands from the customer discussion that okay, he wants some swing, so he understood that. So he noticed that he also has the safety feature in mind. So instead of 2 strings, he gives the third strings also. Third strings also. So he has this basically in his mind and he tells to the marketing planning people that okay, customer wants something like that. It should be, because the second picture is in the mind of the salesperson. He explains to the marketing people. He tells all the description what the customer wanted, that it can be hanged on the tree, it can have basically all the stuff. So what marketing people think, because he noticed that not apart from the swing, 2-3 people can do it. So what is his thinking? So he basically plans like that. So when this planning go to the industry, see how our engineers are designing. They are very particular that don't hang it, just put on the floor, on the ground. So all safety is there. So this is how our engineering people are designing it. So then how manufacturing people are making it and how field services are installing it. See, they are putting 2 strings like that. So actually the customer wanted this, but there is a distortion in the communication or understanding that how sales people, how marketing people plan, how engineers designed it, and how manufacturing and how field services. Ideally, it should be that what the customer wanted, our salesperson should understand accurately, and they keep on asking what you want. If they do not really understand, so whatever, because for the first gap comes between customer and sales, then sales and marketing. So information distortion or requirement distortion goes there. Ideally, it should be like that. What the customer wanted, what the sales order, what the marketing planning did, how the engineers are designing, manufacturing, and how they are installing later. So all basically should be like that. This is what basically the target of the quality function deployment. So in brief, just by one slide, you can understand that UFD targets here. Now some more discussions. There is basically time. I don't think now our children and our grandchildren understand this. Time was when a man could order a pair of shoes directly from the cobbler. So no ready-made shoes were available. We used to go to the cobbler, by measuring the foot himself and personally handling all aspects of manufacturing, the cobbler could assure the customer would be satisfied. Same.
Good afternoon, sir.
Good afternoon.
Okay, sir. Sir, actually, I'm typing, but it's not. It's showing failed to send. Because
But-
if I want to ask questions, how, sir?
Dear participant, please don't interrupt in between the lecture. If you have any query, then you can type it on chat. Otherwise, mail
Okay,
us.
sir.
Okay. Otherwise,
Okay.
mail us. Don't interrupt in between the lecture. Okay.
Okay, thank you, sir.
After
thank
the
you.
lecture. After the lecture, you can ask.
Okay, sir. Also, send your mail ID, sir.
Please, yes, I
WhatsApp number.
please don't
Mail
interrupt.
ID is there. You can see the brochure, na?
Okay, sir. Thank you, sir. Thank you, sir.
Okay.
Sir, you please continue.
Thank you. Sorry, sir, for interruption.
All right. So this is the cobbler example. There are many other examples. Like suppose we go to the tailor, and for stitching to the of our trouser, basically, we go there. We give our clothes to the tailor. He first checks that whether the cloth is sufficient to prepare that trouser. Then what he does, he just takes all the measurement, your waist, your length, and all things, basically type of pocket, type of other things, and he patiently keeps on measuring thing. And what our behavior at the shop of the tailor is, we start giving our commentary. This is a little larger, little less, little this. I want side pocket, cross pocket, that pocket. And the tailor never interrupts us. He patiently listens what our requirement is. So he keeps taking the measurement, like the length 40, you say no 39 or 41. You keep on saying all those stuff. And many times, we, like in the shoes, we never mention what our needs are. He just measure it and we say, yeah, little less, little more, all these things we say. He knows what a customer wants, from me regarding shoe or regarding trouser. Right? Suppose one more example is the car example. When you go to the car dealer, what you do? You say, I want a car, Honda City car, say for example. Okay, you want a car. So you keep on telling him that, okay, I want very good stereo, I want power window, I want this type of wheels, this type of, you can say, the seating arrangement, this type of seat cover, so many things you keep telling. So once he notes down all these things, then he tells you, okay, the total cost of the car will be this much and delivery date is so and so. And when suppose you go there on the delivery date and you say, okay, my car is ready, he says, yes, your car is ready. So you take the key and just goes to the car and you tries to start it, and the car starts also. But when you try to move it, the car is not moving. So when car is not moving, you are really furious. You call that salesman, okay, what's happening? So my car is there, it's not moving. So he says, okay, sir, please listen. This is the list you have provided. What list? Power window there, stereo is there, seat covers are there. Everything that you mentioned is there. You never mentioned that car should run. So what will you say? That is the basic requirement. So there is a difference between two things. One is the spoken requirement, one is the unspoken requirement. And that basically is the QFD. That basically, if you buy a car and that car is not running, it is of no use for you. And that basically quality function development and deployment was developed to bring this personal interface to modern manufacturing businesses. So that personally, that yesterday I was talking customization, that is very important nowadays to survive in the competitive world. It helps organizations seek out both spoken and unspoken need. Many times customer is illiterate. If you ask the customer, okay, what structure you want? I want this structure. What strength you want? Because he doesn't know what is the Newton per millimeter square. He says, बहुत ज़्यादा चाहिए, very high. And what is that very high? That is the capability of the engineers to extract from the customer how he extracts what ज़्यादा means to him. So that is both spoken and unspoken need. Translate these into actions and design and focus various functions. Because now you need to know what exactly you want. So both you need to take care of both the things. QFD empowers organizations to exceed normal expectations. So better thing was that, okay, when you go to the take the delivery of the car, you started the car is running very smoothly, and when you finally settles the account, he says, okay sir, this car cover is free to you. Will you say that I will not take car cover? Because this is above your expectation. He is giving something additional, and that additional basically creates the wow requirement. You are exceeding the normal expectation. That is the QFD. Because many times we do not know what we want, but because the company and the professionals, they know what are the general requirements. If somebody is buying a so expensive car, he needs the cover also. Tailor says, okay, you given the order for trouser. So when you took the trouser from the tailor, he says, sir, your cloth was a little extra, so I prepared a necktie for that. This is free from my side. So that feeling to get something extra that you never expected, that basically gives you an unanticipated excitement. That is normally you say wow requirement. You can take food from any place, from a redi wala, from a restaurant, from dhaba, from a hotel. All the food satisfies you, but with approximately the same cost, if somebody gives you something extra, that creates the value. That is the exceeding the customer requirement. That should be the key. Satisfaction of the customer, that has gone. Every product satisfies you, but point is, what is exceeding your requirement? So if I say what is QFD, there are many ways to define that understanding customer requirement. It is a quality system thinking plus some psychological thing, because you need to understand what the customer wants, plus some knowledge. And unless you have the knowledge, you can't basically read the psychology. And you should have a thinking that is related with the system, that is of quality. Another way to define it, maximizing positive quality that add value to the system. Or you can say it is a comprehensive quality system for customer satisfaction, or you can say for exceeding the customer satisfaction. Or say that QFD, it is a strategy to stay ahead of the game in the present competitive world. Now again some more definitions. So this is a technical definition. That was the broad definition. A methodology for building the voice of the customer into the product. The voice of the customer is the term used to describe the stated and unstated needs or the requirement. So this methodology basically helps you to capture the voice of the customer, what customer wants, stated need or unstated need, and translate into the designer's requirement. So as per my customer requirement, what are the design features I can provide so that my every customer requirement is satisfied. The way to assure the design quality while the product is still in the design stage. Planning tool, some people say QFD is a planning tool used to fulfill customers' expectations. Some information on QFD. It was developed in Japan in the mid-1970s, and it is very common with the Japanese. Anything new, they do it. So they don't tell to the world, they don't publish anything. So for first 8 to 10 years or 12 years, they just get the benefits of that. And once that technology or methodology is basically grown up, then they tell to the world. So by the time they basically enjoy the competition, because they are one who basically developed it and they basically use it. It was introduced in America in the late 1980. So approximately 14 to 15 years, this came to the USA. Toyota, because first the Toyota company basically developed this methodology, they were able to reduce 60% of the cost to bring a new car model to the market. So it basically helped them to reduce the market, not only the cost, but also the lead time between placing the order and receiving the order, plus the exceeding the customer requirement. Toyota decreased 1/3 of its development time. So I mentioned not only that development time, lead time, cost, everything was beneficial, and it is used in cross-functional teams. Companies feel it increased customer satisfaction. Success story. Ford Motor Company. In 1980, the company was as a takeover candidate. They were about to sell everything. So because they were in a continuous loss, and when they came to know this Toyota is applying QFD, so they employed QFD to design Taurus. Taurus is one of the model of the Ford Motor Company. Taurus, a model largely credited with its turnaround. Just one model changed the entire scenario, that it was almost a takeover candidate and now they are in a profit. It was published in the newspaper known as in the England, Britain Daily Mail, like our Times of India. The quote was, setting a mid-90s benchmark in advanced engineering, safety and comfort. Never has a new Ford car been such a pleasure to drive and ride in. That was such a compliment that it received by the Ford Motor Company, that this Taurus basically is just an example of advanced engineering, safety and comfort. Some important points to understand. It should be employed at the beginning of every project, if it is an original or if it is you are redesigning it. Customer requirement should be translated into the measurable design target. Not like that I want strength zyada kam, thoda zyada, thoda kam, something like that. It should be translated that you can really measure. Sometimes some requirement you cannot measure, but that you can convert into the Likert scale. Likert scale basically it varies. Some people use 1 to 5, some people use 1 to 7, etc. It can be applied to the entire problem. Because suppose a car approximately has 7,000 components. So if you keep on applying QFD on every component, so your life has gone. It will take 20, 30 years to design a car. But if you just apply the QFD on a very vital components, then it helps you. So that's why it's mentioned you can apply anything to every entire problem or any sub problem. It says first worry about what needs to be designed, then how. So that basically is the key. When you're capturing the voice of the customer, we should ask what you want. That is, I am asking to my customer, but normally customer don't know. So they say, instead of saying what I want, they basically try to say how my requirement can be met. Like a small kid goes to his mother, he never says, I am hungry. They say, I want what? May say, for example, Maggie. I want pizza. Why you want pizza? Then he says, I am hungry. So if he knows that if I will only say I am hungry, the mother will give you my roti only, and I don't like rotis or sabjis, whatever. So people are becoming smart. So people, instead of saying what they want, actually want, they basically try to tell how my requirement can be met. That is basically you need to have a clear distinction that what customer is saying, whether he is saying what or how. So you need to know that. So that is an important point. And another important point, that is it takes time to complete. It's not like that today you try to apply, develop QFD model, and tomorrow you will get the answer. It takes, because lot of information basically you have to get, and then basically you plan for the manufacturing or service, whatever. Important part in this methodology is capturing the voice of the customer. Because any information that you have captured wrong, it will basically translate into your all the things, because from customer it goes to the sales, to the marketing, to the designer, to the purchase, to the process plant, to the manufacturing, inspection, field service. So many steps are there. If any mistake happened at the first step, it will be replicated in all the steps. So that's why I'm focusing first on the capturing the voice of the customer. It is important to remember that there is no one monolithic voice of the customer. It's not one voice. Examples I mentioned. Customer voices are diverse. In consumer market, there are a variety of different needs. Even within one buying unit, there are multiple customer voices. Children versus parents. Child wants some particular toy. But when parents see that toy, it can be costly. It may have a very sharp edge. So parents notice that it has a sharp edge. They don't want that he should buy this toy. So requirement basically are diverse. You have to see to whom you are addressing. There are even multiple customer voices within a single organization. The voice of the procuring organization, purchasing department. Designer says, okay, I have to satisfy my customer, fine. So customer says, I want 500 Newton per millimeter square, very high strength. So he recommends some particular material because he is more concerned about the customer designer. So when this requirement goes to the purchase department says, sorry sir, this material is not available in India. Or even if it is available, it will be very costly. The cost will go so high that customer cannot pay for that. So within the organization, the voice may change. The voice of the user is different, voice of the purchase department is different, voice of the supporting or maintenance organization may be different. Your manufacturing people say, okay, you purchase the material. When it goes to the manufacturing people say, you have given the tolerance plus minus 0.001, but I do not have any machine that can give the tolerance up to the third place after the decimal. So you need to take care when you are designing that whose voice is this, what best we can do. Customer is always asking best. So you have to see what my competitors are doing, and check what competitors are providing, how best you can do it, because you have to address all the stuff. Development and marketing personnel should ask why until they truly understand what the root need is. So they keep on asking, why you want this, why you want this. He explains, because the product is not in front of the customer. He has something in his mind, so you need to understand what he says, and you should not stop till you fully exactly understand what the customer wants. Then it says, break down general requirement into specific requirement by probing what is needed. So first ask what you want, he tells you general, then in general you keep on asking why, then you make a tree that this product customer wants, okay. What are the specific features he wants, what are the specific colors, variety he wants, that okay, if he's happy with the one color, is he asking for 10 type of variation, like suppose t-shirt is there, I want 10 options to select. So everything you make in an organization type of chart or a tree chart, so that you can know what exactly customer wants. There are many ways to capture the voice of the customer. You can have a direct discussion, you can conduct the interviews, you can conduct the surveys also, you can conduct the discussion with the focus group that okay, this product is for the middle class. So in the middle class, in different areas, maybe in the villages, in the town, in the cities, metros, all this focus group, you can discuss the things. You can basically capture the voice by just observing the market trend or your competitor trend or the competitor strategies or your customers' behavior. If the product is existing, you can also basically capture some of the features using the warranty data. What type, because this product is existing, I want to redesign it because I'm not getting the market. So I want to improve my product. So through the warranty, what type of problem the existing product is having, that helps you that, okay, these are the things that were missing, or maybe some redesigning, like in the car, suppose, say, for example, the redesigning of the steering, say, for example, you can say like that. You can also basically take the data from those people who are basically providing the field services, installing and sale after services. That because when you are installing, so they basically keep noting whether customer is happy or not, what type of initial complaints they are giving, what type of the complaints when it is they are using it, like that, in the entire life cycle of the product. That already I mentioned. I have told you what QFD target is. The methodology of QFD basically is a 4-phase model. And I'm not saying, if somebody can say, sir, you are talking about QFD. Before 1980, everybody, so many lot of products were there in the market. Almost every product satisfies the customer. Yes, everybody, all these 4-phase product planning, every product, basically, every company goes for the product planning. First they design product planning, then they go for the parts planning. Once parts planning are there, then they go for the process planning. And then once process plans are there, then they start production planning. So these are the very standard phases. Every company does it. Important is, I will tell you later. So it's not like that something new is there as far as the methodology is concerned. Any product design and development involves these 4 steps. These 4 phases, basically, only thing is the connection, the phase 1. The QFD basically majorly addresses the phase 1. So all these phases, basically phase 1, phase 2, they are connected. Let's see how they are connected. This is basically a matrix. This is a matrix. And if you see on the left side, this is the customer requirement. That basically is the phase 1, when you are going for the product planning. That customer requirement means you are capturing the voice of the customer. You are converting customer requirement to the design requirement. This is the voice of the customer. This is the voice of the designer. So you have to translate what the customer wants, what the designer can provide to meet those requirements. So the output of this first phase, that is the product planning, is the design requirement. This is the major part where QFD takes place, although it can help other also. So customer requirement, when you are relating it, important part is you need to capture, you need to design that how customer requirement can be translated into the voice of the designer. Then you go to the phase 2. So this output of the first phase becomes the input of the second phase. If you go to the second phase, that is the part planning, the design requirement is here. So now you have the design. Now onward, there is a standard process that earlier also, now also, and in future also, from the design requirement, you basically translate or convert what are the part requirements. So once you know the part requirement, then you go for the process planning. The part requirement, then you go for the process optimization, all the parameter, at what parameter I should plan, feed, speed, depth of cut, like that. You do all those stuff, and then you go for the phase 4. And when you go in the phase 4, basically your process planning, you convert to the production requirement, and finally from production it goes to the prototype first and launching of the production. So these are how the 4 phases are connected. Major role of, or you can say contribution of QFD comes here when you basically are discussing the customer requirement or you are translating the customer requirement into the designer's requirement. There are some tools that these are the, many of you, I'm not going in detail of these tools, and 7 basic quality control tools, these are the 7 management tools. So out of 7, 4 tools of basically are helpful to capture basically the voice of the customer and converting into the designer's requirement. So most of you might have studied all this affinity diagram, interrelationship diagram, tree. These are the management tools to basically analyze the situation. Then comes the house of the quality, the first phase, that is the you can say product planning. It is the most important part of quality function deployment. Most of the QFD projects stop at the house of, means at the first. I told you, very important critical part is the product planning. Once product planning you have done in a detailed manner, then rest of the things basically are very traditional. It is composed of several sections, because that is product planning. Sometimes we also say house of quality. It is a synonymous name. House of quality or the product planning is the same. This is composed of several sections joined together. It is a storehouse of marketing and product planning information, because from marketing the customer requirements are coming, and you are converting into the designer's requirement or the voice of the designer. That phase is known as the product planning phase. Because we say house of the quality, it looks like this. There is some floor area, some 4 walls are there, some slanting roof is there. I will tell you detail what this says. So there is roof is there like that. So basically it looks like an exploded version of the house, and all the information is stored in this house of the quality. It looks like this. It looks like this. That see if I will explain later in the subsequent slides. So it looks like this. How I will tell you how the informations are stored, in which part which information is stored. It basically are like this, components of the house of the quality. The previous figure, basically if you see here, that in block basically I have shown you. Your first step basically goes from here. Who? You should know, first thing is, who are your customer? If you see the right diagram here, so the point that we are discussing is highlighted with the green color, means we are talking about who are the customer. To listen to the voice of the customer, first need to identify the customer. We forget it. I told you there is no monolithic voice. It can be purchase department voice is different, manufacturing department voice is different, even maintenance department voice, because they say that okay, your design is very good, you can manufacture also, but to do the maintenance I have to open up all entire engine, only then I can do the maintenance. So even the regulatory agencies, they are also the party. You develop something, your regulatory agency says no, it doesn't meet the standard criteria. You are BS4, we are talking about BS6. So you need to address all the voice of the customer. So you need to address consumer, you need to address the regulatory agencies, you need to address all the aspects of the manufacturing, you need to address the marketing and sales people, because they are the finally interacting the customer. Anything wrong, basically they have to listen. So they say that okay, we know what customer want, fine, your product design, purchasing, process planning, manufacturing, everything is excellent. But this is what customer really want. You need to add in, or you need to provide that feature. So first you know that to whom you are addressing. So once you clearly understand, then your life becomes easy. Then it says, then come to the first part, that what the customer want, customer needs. So that information is stored here in this red portion, that what the customer want we store in these rows, need to determine what is to be designed. Consumer, how consumer says, Because suppose I am a consumer, I say product works as it should. Product means, suppose I say car should move. That is one thing. Consumer say it should last a long time. The life should be there, reliability should be there, durability should be there. It should be beautiful, aesthetic aspects. So many requirements are there. It is easy to maintain. It looks attractive. Must be incorporated the latest technology. Consumer is saying all the requirement. It should have many features. So consumer says yes, because that is the what you have to identify what exactly customer wants, and that you have to list down. Consumer says like that. List all the demanded qualities at the same level of abstraction. Now manufacturing. Suppose your consumer is manufacturing. If you are dealing with the manufacturing, they say yes, but please design that. As far as customer requirement is there, that is your business to check whether you are meeting or not. But now if you are designed it, make it sure that it is easy to produce. It should use available resources. It should not be like that for some product only we have to buy so many precision machines. It should use standard component and methods. Means you should not design in such a way that a special type of nut and bolt or screws are required and that is not available in the market. We have to manufacture our nut bolt also. So be careful. It should design should provide the minimum waste. If you are talking about marketing people, they say it should meet customer because they are directly interacting the customer. It should meet customer requirement. Easy to package, easy to store, easy to transport. Because sometimes your product is very good. Customer is also happy. Customer comes to you, he see the product and they are happy. They say, okay, now send this product to my house. You do not have a right package material. Even if you have the right package material, your transportation system is faulty. So by the time it reaches to the house, suppose you are buying a television, it creates some scratches on the screen. And the moment the customer sees, I have seen on the shop scratches, TV was right, now scratches are there, I am not going to take it. So they have to listen to that. So basically their concern is the customer. And all this thing, you need to know who your customer and how basically you are dealing with that. That I mentioned how to determine what's, how to determine the what's. Basically we are coming here, just we are here still. I told you many technique, focus group, customer survey, you can have interviews. So you have to formulate the questions very carefully. If redesign, observe customers using existing product. Combine both or one of the approach with designer knowledge, experience to determine the customer wise. Customer gives you 20, 30, 100. Now you have to see what feasible is there, what exactly is the requirement or not. So all these things you have to take carefully. So once you do all these things, then make a list of the customer requirement and write down here. So now you know who the customers are, what they want. Then comes here who versus what. Basically, this is the importance. Out of 10 requirement, which one is the most important, which one is the next important, further next important, or the least important. So you have to generate some weightages. You can use so many techniques. AHP you can use balanced scorecard technique you can rank on ordering methods you can use. So basically all the requirements are there. You can use some survey also. You can collect the data and can convert to the weightage. Say for example, so many requirements are there. Out of all the requirements, there is one requirement, that is the safety. So you know that safety is the most important requirement. So rank wise it is the first, like that. So you need to generate the weightage for your in this area. Then this part is over. Now you have basically filled all the information on this part. Now Now come on this right side. It says now versus what. It is a planning matrix. If you come to this part, now versus what, basically here you are, what you are doing, you are comparing. First you are comparing where you stand, where competitor, maybe you are, suppose you are comparing 2 or 3 competitors. Your competitor A stands, your competitor B stands. So you are comparing your product, existing product, or whatever you thought in the design, how your competitors are behaving, or how the product has different requirement. So basically you make a matrix that my product, somebody else product, somebody else product, that information you rate here. You can, just an example here, 1 to 5, my product, say for example, first requirement does not meet the requirement at all. Whatever the first requirement, suppose the requirement is the safety, my present product does not meet the requirement. If it does not meet the requirement, I will write 1. If it meets the requirement slightly, I will write 2. If it suppose fulfills the requirement completely, I write 5. So these are the ranking scale 1 to 5. So with respect to what customer wants on every row, I basically give the marks or the ranking here, the scale of the ranking. But I am doing what competitor A is doing, what competitor B is doing. So basically we write all those stuff here. So basically here what we do, it's the planning. So not only we do, so what we do, that these are the customer requirements, where we stand, where competitor A, competitor B, or even competitor C. So when we see the entire view, then we basically plan. Okay, suppose, say for example, we have the 4 colors. My product has the 4 color in the market. Customer is asking for more colors, more options. So when you compare with others, then you decide, okay, my competitor A, one competitor is having only 2 color, one competitor has only 1 color. Customer, I already have 4 color and they are asking for more. So I say I should either keep this feature same. My planning is I will provide 4 color, because already I am ahead of the game. So the more color means more facilities you have to build in your company. Maybe you think that, okay, I am very consumer friendly, I will give the 6. So you have to plan it. So all this planning we do on this side. So once you plan, so basically who your customer, what they want, what are the importance criteria of the requirement, this is customer requirement planning you are doing. So once you finish this, then go to this how these requirements can be met. That portion, you write down that to meet this requirement, what design features should be there. The goal is to develop a set of engineering specification from the customer requirements. Each customer requirement should have at least 1 parameter. That is the guideline for this. You should try that every requirement should have a design features that if I change, say for example, in the materials, suppose if I change the solidification rate in the casting, if I increase the solidification rate, the mechanical property basically improves. So like that. So here basically you write down what are the technical requirements that are basically addressing the customer requirement. What are the technical requirements that address the customer requirement? So once you do all these things, then come to it is a relationship metric. Now we are mapping what the customer wants, what the designers say. So suppose there are 10 customer requirement, and say for example there are 5 designers requirement. This matrix will have the cell 10 into 5, 50 cells will be there. Every customer requirement that on one side, and if you just put a matrix here, that you will have 50 cells. Here you have to address this. That's why I am saying what's versus hows. So this basically is a matrix. It depends how many requirements are there, how many hows are there. Multiply that, you will have so many cells. Now, every cell you have to evaluate corresponding to the customer requirement, corresponding to the designer requirement, and you have to develop a relationship, whether these two have some relationship. If it has a good medium relationship, put 3. If it has a strong relationship, 9. If it have a weak relationship, 1. If it doesn't have any relationship, keep it blank. So basically we need to fill this basically matrix that basically addresses what versus house. So once you have done it, then you should know how versus, this is a triangular matrix, how versus how. How versus how, this area. Because now you're checking that, okay, if I increase the temperature, what will be the effect on the other design property? So that basically, that's why, because if it is a triangular, sometimes it is a positive relationship comes, sometimes it is a negative relationship comes. So that's why it has been quoted, mentioned over here. So this part is over. Then finally, so when you are done, now say how much. Again, it's same as the planning. This is a customer requirement planning. This is a designer requirement planning. What is right now where I stand as far as the designer requirement, where my competitor stands, where my another competitor stands, then say, okay, these are the calculations, where I am, where other competitor. Now, should I increase it? Should I remain same? Should I go for less? That basically you have, it's a decision factor. That's why it's mentioned targets. How much? Determine the target value for each engineering requirement. So based upon your planning here, that comparing other and all those stuff, then you decide what basically the target is there. So this is basically all the components of the house of the quality is explained. Guidelines for the successful QFD is to keep the amount of information in each matrix at a manageable level. Because sometimes when you talk about customer requirements are 50, 30 designer requirement. So you will be confused. So make it in a group. Try to have not more than 20 customer requirement, and means you subdivide the QFD that, okay, for this area, one house of the quality, for this another, then you can basically integrate. An individual matrix should not address more than 20 or 30 items, because it will become very complex to address the issues. If doing QFD on a larger, more complex product, decompose its customer needs into hierarchical level. Maybe you say that one matrix is for the performance, one is for the reliability, one is for the durability. So bigger title is performance. Under the performance, what are the requirements? Under the reliability, what are the requirements? So give them the bigger handle, and then basically develop the multi-function deployment, this house of the quality. Now, one quick example of this PFD model to a hotel, just in the service industry, with lodging and dining facility. So as I already mentioned, identify the customer need. The key question asked here is what the customer want or expect. So just I make a list. This basically is a small case study. Reliability. So bigger heading is the reliability. Under the reliability, these 3 sub requirements are there. Responsiveness. These are the just I am first step I am doing. Responsive prompt service. Willingness to help. So that is basically the customer wants. Tangibles, modern equipment, visual appearance, professional appearance. So they basically want that, okay, when a hotel is there, my requirements are like this, that reliability, responsiveness, and tangibles. Then you have to prioritize customer needs. The second step is and conducting competitive benchmarking. So we use the scale of 1 to 7. 1 means poor, 7 means excellent. In between that scale, and we also basically consider the competitor A and B, And all those steps, those general steps that when we are doing the benchmarking for the customer requirement on the right side, planning side, then performance goal, sales point, all these things basically I shown you in the earlier slides. So I will show you what we have done it. Then designer's requirement. Third step is the designer requirement. Now hotel service basically. So they know that what customer wants. So what they are having, front desk. So front desk is the main general point. What features they can provide, designers characteristic. So their staff should be courteous enough. Fast check-in. You don't want to wait over there. You have a proper complaint handling system. Housekeeping is concerned that your room should be clean, your hotel should be clean, timely arrangement, room items are in the order. As far as the food and other things are concerned, food quality, clean, hygienic, sanitation, employee friendliness, and of course the price. So these are the basically designer side. And when you go try to map what customer want, what your designer says, then you can use 1, 3, 10, this thing, like that you can use it. Step 4 basically, constructing the matrix, basically the center where you are mapping. There are 9 requirements, say for example, and 9 hotel service provider. So 63 cells will be there. Those 63 cells basically, you have to basically either must be having strong, moderate relationship or possible relationship, like that. Maybe weak relationship you can say. Or if there is no relationship, then you can put empty. So all these steps that already I mentioned, we did it. Then we prepared the house of the quality. If I show you first, see this, customer needs. Broad category, reliability, responsiveness, tangible. These, under reliability, these 3 service attributes, here service attributes, here service attribute. So first we fill all these things, right? Then we go to the right side. Right side, customer value. This is what customer wants, because we are writing in the scale of 1 to 7. In a scale of 1 to 7. So he is giving maximum more strength to the ranking wise. Correct billing. Correct billing is 7. So customer scale basically prioritizing of the requirement is given here. Then service performance, where we are providing as whatever the requirements are there. When we check what we are doing, we are giving this type of service to the customer. We check the competitors also. Competitor A's rating is this, competitor B rating is this. Right? Then here only the planning is there. So what we are saying that we know the entire picture, where we are, our competitors are there, what customer goals are, customer requirements are there. Now what are our planning, our performance goal. So we are at 5, we want to make it 6. We are at 5, we want to make it 7. So whatever the customer is, even here customer is asking 6, we are planning no, we should provide us a willingness to help. It should be at the top priority also. So here customer is asking 5, we are saying no, 4. So depending upon other things, here basically our decision, you should say. So based upon our decision, then these are the mathematical things, formulas are there. So what is the sale, how much sales basically is possible, what is the improvement, etc. All this thing basically we do. And finally we calculate the relative weightage. Relative weightage in this. And this relative weightage has been plotted on the bar chart, and you can see the maximum weightage is coming over here. So this basically gives you the entire scope that okay, this is our future planning, how we will address the customer requirement, how much sales will be there, but it will be the improvement from the previous point, because from 5 to 6 we are changing. So there will be certainly improvement ratio. Then we calculate all these things. So this is from the customer side. So once this is ready, then we write the designer thing. Because designer has three main things: front desk, housekeeping, food and beverage. Courtesy, fast check-in, fast check-in, complaint handling. All these features we write here. So when we write all these features, so there are, you can see 4 to 6, 9. And 9 is also here, 10 is here. So 9 into 10, 9, you have a matrix of 90 cells, you fill the rating. You fill the rating. 0 means there is no relationship. Correct billing and cleanliness has no relationship. Like that. Suppose 10 here, problem handling, complaint handling has a strong relationship. Correct? So all these things basically from our Likert scale and from our experience, we fill all these things. Right? Now if you go to the top, so again we try to develop the interaction matrix. That is a triangular matrix. Once we do it, then we calculate the total weightages. That for courtesy, what is the importance weight here? What is the importance weight here? All these things. Then the relative weightages we calculate, and then we go for the design requirement. So these basically are the designer requirement. Now, how much courtesy and etc. Because from here we know this is the most important things. This is the most, as far as the design hotel services are there. Employee friendliness. After the calculation, they notice that this is the first and this is the second. Second is but fast check-in. So now you know to address all the requirement, what are the important features, how much weightage you have to give to what, and then based upon that, based upon your management, you can decide the target. Okay. So this basically is the how basically we fill the house of the quality. This is another example that basically this was for the harness. When you basically climb the mountains related with that, similar stuff is there, but only thing is here basically the calculation process is also given. Application of QFD, its primary application has been for planning and managing product development. More recently, it has been applied to different area, healthcare. One of my student has done application of QFD in designing the operation, the bed of the operation theater. The studies examples are available in the literature. Aircraft engine design, Toyota already you know, Ford you already know. Software people started using in software development, hotels, etc. Some of the benefits of adopting QFD have been documented as reduced time to market, innovation faster, reduction in design changes, decreased design and manufacturing cost, improved quality, customer satisfaction, promotes teamwork, provides the document. The last one, the provide documentation, that is very important thing. That now once if you are planning in that way, it's not like that before QFD nobody was planning. Every lot of example product planning was there. But if you are planning the product using QFD, this information is basically a storehouse of the information. So that is saved on your computer. Next time when you are redesigning, customer says, okay, I want just this one requirement changed. So you go back, you open your file, just change that requirement and makes corresponding change and check whether it's feasible or not. You can design the target. So that reduction in the design changes, fast it becomes faster it goes to the market, means lead time to go to the market. And certainly if all these things you are doing, customer satisfaction or customer exceeding the customer requirement is there. This is basically all about QFD, a tool that assists the tracking of customer requirement through all the phases of, because if your first phase is ready, you can very easily develop the part planning, process planning, production planning. Its house of quality pits the voice of the customer against the voice of the designer. It has been applied in several areas. Thank you very much. Now you may ask the questions.
Yes. Sir, someone is asking, does the QFD is related to Lean Six Sigma concepts?
No. Lean basically is a waste minimization. Means slimming of your processes. And Lean and Six Sigma are related. Because slimmer, make minimization of the waste, go for the accuracy, means Six Sigma basically is 3.4 defects per million, means process capability you need to improve. But QFD is basically for designing it. So Lean and Six Sigma basically is the actual part of the manufacturing planning part.
But another question is, sir, how QFD is linked with this Industry 4.0?
How QFD and Industry 4.0? See, every industry needs the product, because whether it is Industry 1, 2, 3 or 4, but 4 industry is there. Industry 4 has to produce the products, or they have to provide the services. So wherever the products are there, wherever the services are there, the QFD is needed. Even it can be, I have seen case study that people have applied in the education also. That what because for education, my students are my customer. So we should know when I am studying, teaching something, so and we can discuss what your requirements are there. You can develop all these things. Even in the development of the curriculum, you can also apply. Yes, somebody has written HR function. Yes, it can be applied. Lot of case studies available. Yes, QFD and Taguchi are not related. Taguchi is basically a methodology for experimentation. QFD is for the planning of the means mapping of the customer requirement with the designers. QFD and TQM. QFD basically is a step towards TQM. TQM is a philosophy. It's a never-ending journey. Suppose you have ISO. This is one continuous improvement. You have 5S. You have QFD. You have other ISO, QFD, 6S, Six Sigma. So basically, you are moving towards TQM. So fine.
Sir,
So please.
Another query is there any difference between QFD and TQM?
That was I was explaining that TQM is a bigger umbrella. QFD is a part. If your company is using QFD in product planning, means you are moving towards TQM.
Any query? Sir, one query. This is Abhishek Bala. What if 50% customer like a product quality and 50% don't? Then how QFD will be applied?
See, it's not a 50% or not that way. That if somebody doesn't like, they will never purchase it. Why they are purchasing? Why are they purchasing? So it's not a silly question. So if they don't like it, okay, enjoy it.
Sir, how QFD will be useful in software development, sir?
Software development basically, wherever there are two parties are involved.
Okay.
One whose requirement is there, who's providing the requirement, like the designer. Suppose I am a software developer. You come to me, I say, okay, what type of software you want? It should address this, it should address this, it should be very fast. So all those things you are telling to me.
Okay.
And I am just understanding your requirement. Then I am developing the algorithm, and this but how I can provide, how can I satisfy you? Yeah, so it's very nowadays QFD and software case studies are already have some available, but it is a very good research area that you can do it.
Okay, sir. Thank you, sir. Thank you.
Okay, thank you.
So one more query, sir. What is the percentage of accuracy of QFD to analysis customer voice? to analyze the customer voice?
See, it again, that is a very fuzzy, I should say, question. That depends. You know that earlier marketing people were, आप लोग सब छोटे उम्र के हैं. अगर आप, if you go 30 years back, 30, 40 years back, marketing people are very smart people. They know very good English. All those things they are having. They are interacting in a very fancy manner. But now after that, people have noticed that they do not understand the technical, because those who are very smart, handsome and so, they were employed in marketing because they are meeting the people. But when customer says anything, they are not able to understand. So that's why they are employing the technical people. Even now, if you see, most of the marketing people are the top technical people, because they need to understand. So if any accuracy is there, suppose I am an engineer, I am in marketing. If I interact my customer and I am able to that, even 1% of inaccuracy is in my understanding, that 1% accuracy will reflect in the final product. Because if 99% I could only understand right, then when I will tell to the designer, so chances of distortion of the things will go, basically, cumulative effect will be very bad. So it has to be 100%.
Okay, sir. Any query? No. So thank you, sir, for speaking to the participants about the quality function development, and different aspects of QFT have been covered with a very good case studies. So the participants who attended this session really enjoyed your presentation. I hope participants will be benefited with the knowledge in future. So on the behalf of the organizing team, I appreciate for making time from your busy schedule to speak with the participants. Thank you again for your time, sir. Thank you.
Thank you, Dilbag. Thank you, Viral. Thank you very much.
Thank you. Thank you.
Dear participant, for today we are closing the session. Now we will meet tomorrow at 10 a.m. in the morning. Thank you all.
Hello, hello,
Yes,
hello,
I speak.
hello.
Speak, what's the problem?
Hello.
IMC से